Hello and welcome back to Haience, the place where humanity meets science and where curiosity can gently lead you into a world of wonder. Quantum leaps. How quantum physics is changing our world. A realm beyond intuition. Physics has long guided our understanding of nature, from the predictable motion of planets to the mechanics of machines. But today, I invite you on a gentle journey into a realm far stranger and more fundamental than our everyday experience, the quantum realm. Here, at the scale of atoms and subatomic particles, the rules of classical physics we find so intuitive give way to a new property, often counterintuitive set of rules. As Nobel laureate Niels Bohr once remarked, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. This realm defies common sense. Particles can exist in multiple states at once, influence each other instantaneously across vast distances, or pass through barriers that would stop them in the classical world. It's a place where our everyday intuitions falter, truly a realm beyond intuition. Yet, quantum physics isn't just an abstract theory confined to laboratories. It marks a profound paradigm shift in science. Classical physics, the physics of Newton's laws, balls and springs and orbits of planets, wonderfully describes the macroscopic world we directly perceive. In that familiar classical picture, objects have definite positions and speeds. Causes lead deterministically to effects, and nothing can influence something else faster than light. But at the tiny scales of atoms, electrons, and photons, experiments have shown that a new set of rules takes over. In this quantum domain, particles act like waves of possibilities. Outcomes are fundamentally probabilistic. Wow, that is everything. A quantum particle is set to be alive. This was such a dramatic departure from classical thinking that even Einstein was deeply unsettled, famously saying, "I am convinced God does not play dice with the universe," expressing his discomfort with quantum randomness. And entities separated by great distances can exhibit mysterious connections. To that, Bohr wryly replied that Einstein should stop telling God what to do. In short, quantum physics forced scientists to reimagine reality's foundations. Why should we care about these bizarre quantum effects? Because however abstract they may seem, quantum physics is not just theoretical, it's very real and is increasingly woven into the fabric of modern technology and our daily lives. Over a century ago, quantum theory originated from attempts to explain puzzling experiments. Max Planck's work in 1900 suggested that energy comes in discrete packets, which he called quanta, a radical idea that launched quantum physics. In 1905, Albert Einstein used quanta of light to explain the photoelectric effect, laying groundwork for devices like solar panels. These early quantum leaps in understanding soon led to transformative inventions: lasers, transistors, microchips, LED lights, and MRI scanners. Technologies that power the modern world all operate on quantum principles. And now, in the 21st century, quantum physics is driving a new revolution. Quantum computing and quantum communication promise to upend computing, encryption, and more. In essence, the once abstract quantum theory is becoming the basis of very concrete innovations. We truly stand at the dawn of a quantum age. Before we begin our journey, let's outline where we are headed. First, we'll gently introduce the mind-bending basics, the core concepts of quantum mechanics that make it so different from everyday experience. We'll use simple language, vivid examples, and even a few stories to make these ideas intuitive. Don't worry, no complex equations here, just an exploration of concepts like quantization, wave-particle duality, superposition, think of Schrödinger's cat, entanglement, Einstein's spooky action at a distance, dot, and quantum tunneling. Next, we'll take the big leap into how these strange principles are being harnessed in quantum computing, arguably the most exciting technological application of quantum physics today. We'll devote a substantial portion of our time to quantum computing, explaining what qubits are, how quantum computers work in concept, and what incredible things they might do, from revolutionizing drug discovery to cracking encryption to boosting AI. We'll also acknowledge the challenges faced in building these machines and survey the current landscape. Who's building quantum computers and how far have we come? After that, we'll look beyond computation to other emerging quantum technologies, quantum communication for ultra-secure messaging, quantum sensing for extremely precise measurements in medicine, navigation, and science, and new quantum materials that could transform energy and electronics. Finally, we'll slow down and reflect on profound philosophical questions raised by quantum physics. What does quantum mechanics tell us about the nature of reality? Does the act of observation truly influence outcomes? Are there parallel universes from each quantum event? And could quantum processes be linked to something as enigmatic as consciousness? We'll consider these fascinating questions and famous physicists' opinions in an open-minded but clear way, highlighting that there is still no single agreed-upon interpretation of what quantum mechanics means. By the end of our journey, I hope you'll not only grasp how quantum physics is changing our world technologically, but also appreciate the sense of wonder it brings about our universe. So, make yourself comfortable as you listen. Whether you're relaxing in bed or lounging on a cozy chair, and let's take a deep, calming breath. We're about to dive into a world of quantum leaps and curious tales, where reality is stranger than fiction. The mind-bending basics. Welcome to the quantum world. To understand the quantum revolution underway, we first need to understand the weird core concepts of quantum physics. How exactly does the quantum world differ from our everyday classical world? Let's ease into it step by step, comparing quantum versus classical pictures and then unpacking the key phenomena one by one. Throughout, we'll favor simple analogies, everyday examples, and the insights of famous physicists who grappled with these mysteries. So, welcome to the quantum world, from definite states to probabilities, quantum versus classical. In our classical world, objects have well-defined properties. For example, imagine a tiny marble rolling on a table. At any moment, it has a definite position and speed. And if we knew those precisely, we could in principle calculate exactly where it will go next. In classical physics, things are deterministic and knowable. The marble is either here or there, not in multiple places at once. And we assume it exists whether or not someone is looking at it. But in the quantum world of electrons and photons, this certainty evaporates. Quantum particles do not have definite values for certain properties until they are measured. Instead, they exist in a hazy blend of possibilities described by a wave function, a kind of mathematical cloud of probability. An electron, until observed, doesn't have a single exact position. Rather, it has various probable positions. In fact, observation affects reality in quantum mechanics. When we measure the electron's position, the wave of possibilities collapses to one definite outcome. This is profoundly different from a marble that simply has a position whether we measure it or not. Another stark difference: classical objects follow continuous paths and can have any amount of energy or momentum, whereas quantum systems often have quantized, discrete values they can take. In classical physics, energy can vary smoothly. Think of a car that can move at any speed: 10.0 kilometers per hour, 10.1 kilometers per hour, 10.2 kilometers per hour, and so on. But in quantum physics, certain quantities, like the energy of an electron in an atom, can only take specific allowed values. Nothing in between. It's as if that car could only go exactly 10 or 20 or 30 kilometers per hour, and not at intermediate speeds. This quantization was one of the first clues that a new physics was at play. As we'll see, it's akin to climbing stairs rather than walking up a ramp. You must step to the next stair, a discrete jump, rather than slide continuously. In summary, the classical world is like a well-behaved library where everything has its place and stays put until moved, whereas the quantum world is more like a surreal art gallery with shape-shifting exhibits that don't solidify until you glance at them. Keep this contrast in mind as we explore specific quantum concepts. Each of these concepts shocked the scientific community when discovered, and together they form the foundation of quantum mechanics. Key quantum concepts. Explained simply, let's break down the most important quantum phenomena one by one. Using easy-to-grasp analogies and the occasional story, these ideas, quantization, wave-particle duality, superposition, entanglement, and tunneling, are the pillars of quantum physics. Don't worry if they feel counterintuitive at first. Even the great pioneers found them bizarre. As Richard Feynman humorously noted, I think I can safely say that nobody understands quantum mechanics. He meant that in a deep, intuitive sense. We can use quantum theory extremely well, but what it says about reality can be mind-bending. So, if it feels strange, you're in good company. Let's start with the idea that gave quantum theory its name: quantization, the world in discrete steps. In 1900, Max Planck was studying a puzzling problem about how hot objects emit light, known as blackbody radiation. Classical physics predicted wildly incorrect results, dubbed the ultraviolet catastrophe. Planck found he could fix the theory by assuming that energy wasn't exchanged continuously, but in discrete packets called quanta. This was a radical suggestion. It's as if light, normally thought to be a continuous wave, could only come in chunks, like grains of sand. The term quantum literally means a quantity or packet. To visualize quantization, imagine walking up a gentle ramp versus a staircase. On a ramp, you can stand at any height continuously, but on a staircase, you can only stand on the discrete steps. You jump from one step to the next. Similarly, an atom's electrons can only occupy specific energy levels, like specific rungs of a ladder, and not values in between. When an electron quantum jumps from one level to another, it either absorbs or emits a packet of light, a photon, with energy exactly equal to the difference between those levels. The phrase quantum leap ironically has entered everyday language to mean a giant change, but in physics, a quantum leap is the smallest possible change, a single step between quantized states. It's mind-bending. Energy, Planck himself was uneasy with this at first, but Einstein's 1905 work on the photoelectric effect, showing that light itself can behave like particles called photons, cemented the idea that quantization is real, which we experience as smooth and continuous. Turn up a dimmer switch and light increases smoothly. At microscopic scales, comes in indivisible units. Today, we know quantized energy levels underlie why atoms emit only certain colors of light, spectral lines, and why electrons orbit nuclei stably. If energy weren't quantized, atoms would be unstable. Quantization provides the graininess of the quantum world, a first departure from classical continuity. Think of it as nature's pixelation at ultra-small scales. Wave-particle duality, light and matter's double identity. Is light a wave or a particle? Are electrons particles or waves? For centuries, experiments flip-flopped on the nature of light. Newton thought particles, Huygens thought waves. By the 1800s, Young's double-slit experiment showed light produces interference patterns like waves do, strongly indicating wave behavior. But then Einstein's explanation of the photoelectric effect in 1905 showed light comes in particle-like packets, photons, to kick out electrons from metal. The astonishing truth revealed by quantum mechanics is that light is both a wave and a particle. And not just light, everything is. This is the concept of wave-particle duality. It means an electron, which we normally think of as a little particle, can exhibit interference like a wave under the right conditions. Let's understand this through the famous double-slit experiment, which Feynman called the central mystery of quantum mechanics. Imagine a simple setup. You have a wall with two narrow parallel slits, and another screen behind it that records whatever hits it. First, in a classical analogy, throw tiny balls, like sand grains or tennis balls, at the wall. Most hit the wall, but some go through the slits. On the screen behind, you'd see two clusters of hit marks directly behind the slits, basically two bright bands corresponding to the two slits. That's the pattern particles would make, two piles. Now, instead, send waves through the slits. For example, water waves in a tank or light waves. Each slit acts like a new source of ripples, and the waves from the two slits overlap and interfere. Where a crest meets a crest, they reinforce to make a bigger crest. Where a crest meets a trough, they cancel out. On the screen, or a detector measuring wave intensity, you'd see an interference pattern, a series of alternating bright and dark bands for light, or high and low wave intensity regions. This pattern is distinct. It has many stripes, not just two blobs. It's a fingerprint of wave behavior. Now for the quantum magic. Fire electrons one by one at the double slits with the detector screen behind. ... Electrons have mass and were historically considered particles. If you send them one at a time, you might expect them to either go through left or right slit and hit the screen like little pellets, eventually forming two clumps, like our sand grains. At first, as a few electrons hit, you see seemingly random dots. But as more and more electrons accumulate on the screen, a pattern emerges. And shockingly, it's the interference pattern of two overlapping waves, with multiple bands. Each electron, although arriving as a tiny localized dot on the screen, collectively builds up a wave-like interference pattern, as if each electron somehow went through both slits and interfered with itself. This happens even if you send the electrons one at a time, so they can't be interfering with each other. Each electron individually behaves like a delocalized wave when not observed. It's as if each electron is everywhere it could be, going through both slits until it's detected, at which point it appears at a single spot. This is mind-bending. Electrons and photons, atoms, etc., travel as waves of possibility, but hit like particles. Now the plot thickens further. Add a detector at the slits to observe which slit an electron passes through, trying to catch it in the act. The very act of measuring destroys the interference. If you determine an electron went through the left slit or right slit, ... The pattern on the screen reverts to two simple clumps. No interference. It's as if the electron, knowing it's being watched, decides to behave like a particle and not a spread-out wave. Stop measuring, and the interference pattern comes back. This dramatic result shows that observation affects behavior, a core part of the infamous observer effect in quantum mechanics. The double-slit experiment encapsulates wave-particle duality and the measurement problem. Quantum entities have a dual nature, manifesting as distributed waves or localized particles depending on the experimental setup. They are both and neither, in a sense, until measured. As one science writer put it, the double-slit experiment is universally weird. It forced us to accept that reality at small scales doesn't follow classical either-or logic. An electron is not simply a little billiard ball. It's described by a wave function that encodes probabilities of finding it in various places. And that wave can interfere and produce very non-classical outcomes. This experiment so perplexed physicists that it took decades to digest. Louis de Broglie, in 1924, proposed that matter has wave properties. He assigned a wavelength to particles based on their momentum. And soon after, experiments confirmed electrons do produce interference like waves. Conversely, light, undeniably wave-like in interference, also comes in particle units, photons, as evidenced by discrete detections in sensitive cameras. We are thus stuck with the poetic truth that everything we call real is made of things that cannot be regarded as real, in the words of Niels Bohr. By that, he meant our classical concepts of particle and wave are just inadequate. Quantum objects are sui generis, with their own unique behavior. Wave-particle duality is a cornerstone of quantum mechanics. It means context matters. How you observe something dictates what aspect you see. To summarize with an example, light traveling through space acts like a spread-out electromagnetic wave, capable of interfering and diffracting, but when you detect it on a screen or sensor, it deposits its energy in lumps, photons, at particular points. Likewise, electrons in an atom behave like standing waves, giving discrete energy levels. But a detector, clicking to register an electron, finds a whole electron in one spot. As observers in a quantum world, ... we must embrace this duality. As one witty physicist quipped, anyone who isn't shocked by this has not understood it. But it's real. It's been demonstrated over and over that quantum entities transcend classical categories. Superposition, being in many states at once, Schrödinger's cat paradox. Perhaps the strangest concept in quantum mechanics is superposition. This is the idea that a quantum system can exist in multiple states simultaneously until it is measured. It's a direct consequence of the wave-like nature of quantum objects. Remember those probability waves? Well, a particle's wave function can be a combination, a linear combination of states. For example, an electron's spin, a tiny magnetic orientation it has, can be up, down, or in a superposition of up and down. In fact, until measured, the electron's spin is both up and down at the same time in a well-defined way. It's in a limbo of possibilities. Only when a measurement is made, say by passing it through a magnetic field and forcing it to choose, do we get a definite up or down result. Before measurement, it isn't correct to say the electron has one or the other property. It truly has both potentialities. This isn't due to ignorance, like saying, I don't know which until I look. The quantum formalism insists the electron genuinely occupies a state that is a blend of multiple outcomes. This is what we mean by superposition. The particle exists in all the possible configurations at once, weighted by probability amplitudes, until interaction with the outside, observation, causes it to assume one concrete state. Superposition is a hard pill to swallow. To illustrate the weirdness, in 1935, Erwin Schrödinger, one of quantum theory's founding fathers, proposed a now-famous thought experiment known as Schrödinger's cat. He wanted to highlight how absurd the idea of applying quantum superposition to everyday objects seems. Imagine a closed steel box containing a cat, along with a very contrived, lethal mechanism. Inside is a tiny bit of radioactive material, a Geiger counter, and a vial of poison gas. The setup is such that if a single atom of the material decays, a quantum event that is probabilistic, the Geiger counter triggers a hammer that breaks the vial, releasing poison and killing the cat. If no decay happens in a given time, the cat lives. Now, according to quantum mechanics, that radioactive atom's decay is a quantum event that can be in superposition. Decayed and not decayed at the same time until observed. This means, if you believe quantum theory, the whole system, atom plus cat, can evolve into a superposition. One branch where the atom decayed and cat is dead, and another branch where the atom did not decay and cat is alive. Thus, the cat would be in a superposition of alive and dead prior to someone opening the box to check. Schrödinger intended this scenario as a reductio ad absurdum of the prevailing Copenhagen interpretation, which says the wave function collapses on observation. He did not literally believe a cat can be both alive and dead. He was pointing out that quantum theory, when taken at face value, suggests a macroscopic absurdity. In everyday life, we never see such superpositions. A cat is either alive or dead, never both. So what gives? The resolution in practice is that decoherence and measurement by the environment ensure that macroscopic superpositions like that don't persist. They collapse incredibly fast. A cat scenario was meant to illustrate the measurement problem. At what point does a quantum possibility become a single reality? Is it when a conscious observer looks? When the Geiger counter registers? When particles from the environment interact? This remains philosophically debated. Schrödinger's cat, paradoxical as it sounds, has become a shorthand for quantum superposition. People say it's like Schrödinger's cat to describe something indeterminate or unresolved. In less dramatic terms, superposition underlies much of quantum behavior. A quantum particle is described by a wave function that can be a superposition of eigenstates, definite states. For instance, take an electron in an atom. it might be in a superposition of two energy levels, meaning it has some probability of being found in one or the other if measured. While in superposition, it's not in a single energy state. It truly occupies both potential states simultaneously. We can even observe interference between the possibilities. Only when a measurement is made, like detecting the electron's energy or its position, does the superposition collapse to a definite outcome. Prior to that, the system evolves according to the Schrödinger equation, which linearly combines all possibilities. To give a more everyday analogy, imagine flipping a coin. Classical common sense says the coin is either heads or tails after it lands. Whether or not you work, it's just unknown to you until you check. But a quantum coin, were there such a thing, could be in a superposition of heads and tails at the same time. Literally both, until observed. It's not that it's one and we simply don't know. It's truly undetermined and in both states. When you look, you force it to be one or the other. As another analogy, think of a very clear tone musical instrument playing two notes at once. You might hear a beat or interference pattern because the sound wave is a superposition of two frequencies. If you measure one aspect, you might force it to pick one frequency. Similarly, superposition in quantum systems can produce interference effects, like in the double-slit experiment. Each electron interfered with itself via superposition of paths. The concept of superposition is central to the power of quantum computing, as we'll see later. A quantum bit, qubit, can be 0 and 1 at the same time, in superposition, which allows quantum computers to process many possibilities simultaneously. But it also raises deep questions about reality. Does the particle decide its fate when we look? Is it our knowledge that's uncertain, or the particle's actual existence? The mainstream view, the Copenhagen interpretation, is basically pragmatic. The wave function superposition is a complete description of the system prior to measurement. And upon measurement, it randomly yields one of the outcomes with probabilities given by the wave function. Some physicists, like Einstein, didn't like this fuzziness. Einstein, Podolsky, and Rosen, EPR, argued in 1935 that quantum mechanics, in allowing such superpositions, might be incomplete. Schrödinger's cat came out of discussions between Schrödinger and Einstein, highlighting how quantum superposition challenges the nature of reality. Nonetheless, countless experiments with particles, not caps, have confirmed that superpositions are real. For example, electrons have been put in superposition of being in two different places a noticeable distance apart at the same time in interference experiments. Even molecules with dozens of atoms have displayed interference, acting as quantum waves. So while we don't see a cat in a blurry, alive, dead state, small systems absolutely do exist in multiple states at once. We'll later mention interpretations like many worlds that try to explain this by saying both outcomes happen, but in separate universes. For now, the key takeaway is, in the quantum world, objects exist as probabilities and potentialities simultaneously. Reality at small scales isn't a single track, but a blur of possibilities that only sharpens to a definite fact when an observation or interaction forces a choice. Superposition is the heart of quantum weirdness. It allows a particle to explore multiple options in parallel, a bit like having your cake and eating it too. until the universe checks in on which you actually did. Entanglement, spooky action at a distance. If superposition sounds strange, entanglement takes quantum oddness a step further by linking two or more particles so that they share a combined state, meaning one cannot be fully described without the other. Even if they are far apart, entangled particles have their properties correlated in a way that defies classical intuition. Changes to one seem to instantaneously affect the other, no matter the separation, which led Einstein to dub entanglement spookhafte Fernwirkung, or spooky action at a distance. Imagine two photons that are emitted from a common source in an entangled state. For example, their polarizations are linked such that they are always opposite. One is vertical when the other is horizontal. Say, until you measure them, they exist in a superposition of both possibilities together. Neither has a definite polarization on its own. Only the combination is defined. Now, if you send one photon to New York and the other to London, and you measure the New York photon's polarization, you instantly know the London photon's polarization. It will be the opposite. It's as though the measurement of one collapsed the state of both instantaneously. This is puzzling because no signal or causal influence can travel faster than light according to relativity. But entanglement correlations seem to transcend distance. They are non-local. However, and this is crucial, entanglement cannot be used to transmit information faster than light, so it doesn't actually violate relativity. It's spooky because it's instantaneous correlation without communication. But if you try to use it to send a message, no, you find you cannot control the outcome on your end to encode a message. The results are random. The universe only guarantees that if you and a friend later compare your measurements, they will be correlated in a certain way. So there's no usable signal going faster than light, just a mysterious connection. A common way to entangle two photons is via a process called parametric down conversion. A laser photon goes into a special crystal and comes out as two lower energy photons whose polarizations are entangled. To unpack this, let's consider a concrete example with entangled photons. Suppose the photons are prepared in an entangled state such that neither photon has a definite polarization, vertical or horizontal, on its own. They exist in a superposition. But we know that if one is measured vertical, the other will always be found horizontal, and vice versa. We then separate these photons. According to quantum mechanics, their joint state is something like photon A vertical, photon B horizontal, plus photon A horizontal. Photon B vertical equals √2, a superposition of the two opposite polarization possibilities. Now, say Alice measures her photon A in a certain polarization basis. She will get a random outcome, vertical or horizontal, each 50% likely. But at that very moment, Bob's photon B on the other side instantly collapses into the opposite state. If Bob later measures B in the same polarization basis, he will get the opposite of whatever Alice saw. It's as if the photons shared a secret, such that the moment one reveals its identity, the other adjusts to complement it. This holds even if the photons are light years apart. Experiments by Elaine Aspect in the 1980s and many since have demonstrated entanglement with particles separated by large distances, confirming these correlations are real. In 2022, The Nobel Prize in Physics was awarded to Aspect, Clauser, and Zeilinger for groundbreaking experiments confirming entanglement and ruling out local hidden variable explanations. In other words, they showed the correlations violate certain inequalities, Bell's inequalities, that any local realistic theory would obey, thus solidifying that entanglement is indeed a non-classical phenomenon. Why did Einstein find this spooky? Because it implied that quantum mechanics is not locally real. You cannot think of each particle as having its own pre-existing definite state, independent of observation. Their joint state is what's real. Einstein, along with Podolsky and Rosen, in 1935, published the EPR paradox paper, arguing that if quantum mechanics is correct, it seems to violate locality or to be incomplete. They hoped some deeper theory might explain the correlations without spookiness. But to Einstein's dismay, experiments decades later showed quantum mechanics was right. Nature really behaves this way. Entanglement means the entire system must be considered. The parts do not have independent existence in terms of certain properties. As a dramatic metaphor, imagine you have two coins that are entangled such that they always land opposite. Toss one in New York and one in London, and each coin by itself is random heads or tails. But whenever you later call your friend and compare, soapbox. You'll find one got heads and the other tails every time. No matter how far they seem synced. But you couldn't use it to send a message because you can't make your coin come up heads or tails at will. It's random. The outcome is only correlated once compared. Entanglement isn't limited to two particles. You can entangle many. It's the essential resource in quantum computing and cryptography. The spooky part is simply that the quantum state is holistic. Another way to say it, measuring one particle instantly affects the knowledge of the system state, and the wave function collapses globally. But physically, no energy or signal travels between them at measurement. Still, it's deeply counterintuitive. As Schrödinger himself said in 1935, entanglement is the characteristic trait of quantum mechanics that enforces its entire departure from classical lines of thought. Once particles interact and become entangled, they, in effect, share a single quantum state. No matter how far apart, they remain a unified system in terms of that state, until something, like a measurement or environment, breaks the entanglement. What are the implications of entanglement? Philosophically, it challenges the notion of separability, that objects have their own independent states. In quantum reality, when two particles are entangled, the state of one is tied to the state of the other. Information-wise, it enables amazing applications, quantum teleportation, transferring a quantum state using entanglement and classical communication, and quantum cryptography. We'll discuss later how entanglement can secure communications. It also implies that the universe at a fundamental level might be an interconnected web of relations rather than isolated building blocks. Einstein never fully reconciled with entanglement, but today we accept it as a well-demonstrated aspect of nature. In summary, entanglement means two particles can have a fused fate. Even miles apart, they behave as one in certain respects. This concept will return when we talk about quantum computing. Multiple qubits are entangled to perform computations. And quantum communication. Entangled photons enable ultra-secure encryption. It's one of the most non-intuitive yet experimentally verified features of quantum mechanics, truly earning the nickname spooky action at a distance. Quantum tunneling, the ghostly passage through barriers. In the classical world, if you don't have enough energy to overcome a hill or barrier, you simply can't get past it. A ball won't roll over a hill unless it's given a push that's high enough. Quantum particles can do something classically impossible. They can tunnel through barriers even when they seemingly don't have enough energy to climb over. Picture a ball in a valley separated from another valley by a hill. Classically, if the ball doesn't roll with enough speed, it'll never reach the other valley. Quantum mechanically, the ball, or rather, a particle, has a finite probability of appearing on the other side, as if it dug a tunnel through the mountain. This is quantum tunneling, a direct consequence of the Heisenberg uncertainty principle and the wave nature of particles. A particle's wave function isn't strictly zero on the other side of a barrier, even if classically forbidden. There's a small leakage of the wave function, which means a non-zero probability of finding the particle beyond the barrier. The thicker or higher the barrier, the smaller the probability. But it's never strictly zero for finite barriers. Tunneling might sound like a novelty, but it's extremely important in both nature and technology. Why does our sun shine? Classically, two protons repel each other strongly, both positive charge, and at solar core temperatures, around 15 million Kelvin, they don't have enough energy to overcome the electrostatic repulsion barrier. At its core, hydrogen nuclei protons need to fuse to form helium and release energy. Without a quantum effect, fusion would be impossibly slow, and the sun wouldn't burn as it does. However, quantum tunneling allows protons to get close enough to fuse occasionally despite not having enough classical energy. It's through this tiny but crucial tunneling probability that fusion proceeds in stars at the observed rates, enabling starlight. In essence, particles borrow a bit of uncertainty and energy to sneak through the barrier, a manifestation of the uncertainty principle. Energy and time have an uncertainty relationship that allows brief fluctuations. In our everyday technology, a great example is the Scanning Tunneling Microscope, STM. This device, invented in the 1980s, allows us to literally image individual atoms on surfaces. It works by bringing an extremely sharp metal tip very close to a surface. When the gap is just a few atoms wide, electrons can tunnel through the vacuum gap from the tip to the surface, or vice versa, even though classically they shouldn't. Vacuum is an insulator. By measuring the tunneling current as the tip scans across, we get a map of the surface at atomic resolution. Those iconic images of rows of atoms were made possible by electron tunneling. Another mundane example, flash memory, like USB drives and SSDs, uses tunneling to store and erase data. In flash memory transistors, a thin insulating barrier separates a charged storage layer. To write or erase data, electrons are quantum tunneled through that insulating layer via a high voltage onto or off the storage node. The barrier is thick enough that under normal conditions, the electrons stay trapped, retaining data, but under a strong electric field, some will tunnel across. Without tunneling, we wouldn't have the convenient, non-volatile memory that powers our devices. Quantum tunneling also sets practical limits. As we make electronic components, like the transistors in computer chips, ever smaller, the barriers, gate oxides, etc., become so thin that electrons start tunneling through when they shouldn't, causing leakage current. This is one reason there's a limit to how miniaturized silicon transistors can get. Tunneling becomes a problem, or sometimes a useful tool. Engineers have to account for quantum effects in modern electronics design. A more futuristic application. Tunneling diodes and devices use tunneling intentionally for high-speed electronics. Also, experiments in quantum computing often involve Josephson junctions, basically tunneling junctions for superconducting Cooper pairs, paired electrons, to create qubits. So tunneling is part and parcel of advanced quantum tech. Perhaps a simple analogy. Think of a ghost walking through a wall. Classically impossible, but a ghost might do it. Quantum particles are not ghosts. But their wave nature means they aren't like solid billiard balls. There's a chance they can appear on the other side of a barrier. Another analogy. Imagine yourself confined in a room with walls. Classically, you can't escape without enough energy to break a wall. But if you were quantum, there'd be a minuscule chance you'd suddenly find yourself in the adjacent room without breaking anything, simply by the weird rules of your wave function. For macroscopic objects, that probability is so absurdly tidy, it's effectively zero. You will not spontaneously quantum tunnel through your bedroom wall. The odds are astronomically against it, but for electrons or nuclei on small scales, those odds become significant. In fact, radioactive decay itself is often a tunneling process. An alpha particle in a nucleus tunnels out through the nuclear force barrier to escape as radiation. In summary, quantum tunneling is a striking example of how quantum mechanics defies classical common sense. Particles can sneak through barriers by virtue of their wave-like spread and the uncertainty principle. This is why certain unstable atoms decay at the rates they do. Tunneling probabilities dictate the half-life. It plays a role in phenomena as grand as the shining of stars and as down-to-earth as the memory stick in your pocket. It is yet another reminder that at a fundamental level, nature's rules permit things that a purely classical viewpoint would forbid. We've now toured the core mind-bending concepts of the quantum world. Let's pause to reflect on what we have. Quantization. Nature is granular at small scales, with discrete allowed values. Wave-particle duality. Quantum entities behave as both waves and particles. Depending on context, superposition. A single system can exist in a combination of states, both at once, until observed. Entanglement. Particles can have linked fates, creating correlations across space that puzzle our sense of locality. And tunneling. Particles can do classically impossible feats, like crossing barriers without the requisite energy. Each of these was verified through ingenious experiments, and often initially met with skepticism or confusion. Together, they formed the basis of quantum mechanics, which by the 1930s had matured into a robust theory. The world of the very small is strange indeed, but it's also extremely successful at predicting outcomes. Quantum mechanics quickly became the foundation for chemistry, solid-state physics, and much of modern science. As bizarre as it sounds, it's been tested to incredible precision, to many decimal places in some cases, and never once failed within its domain. Renowned physicist Richard Feynman expressed both awe and acceptance of quantum theory with a famous quote we encountered earlier about understanding it or not. He also gave a prescient insight relevant to our next section. Nature isn't classical. Damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. In other words, to truly harness the power of these quantum principles, we might need to build machines that themselves operate on quantum rules. This idea, proposed by Feynman in the 1980s, is at the heart of quantum computing. So, having grasped the quirky rules of the quantum realm, let's turn our attention to how these rules can be used to do remarkable things. Specifically, how is quantum physics poised to change computing and technology in a revolutionary way? In the next section, we'll take the big leap from theory to practice, exploring the quantum computing revolution, where superposition and entanglement become resources for computing power, and quantum leaps go from metaphor to real machines. The big leap, the quantum computing revolution. Of all the applications of quantum principles, quantum computing stands out as one of the most transformative and exciting. It's often billed as a revolution in technology, a new kind of computing that could tackle problems utterly infeasible for classical computers. By exploiting the very weirdness, superposition, entanglement that we discussed, in this section, we'll gently explain what makes a quantum computer fundamentally different from a classical one. We'll introduce the idea of the quantum bit or qubit and how it can be 0 and 1 at the same time. We'll discuss conceptually how quantum computers operate without diving into too much math. Highlight what extraordinary tasks they might accomplish, from designing new drugs to cracking encryption to supercharging AI, and also give a reality check on the current state of the field. Hint, we are in the early innings, impressive progress, but still lots of challenges to overcome. By the end, you should understand why there's so much buzz around quantum computing and how it directly stems from the quantum phenomena we've learned about. From bits to qubits, superposition in computing. Revisit how your classical computer or phone works. It processes information using bits, tiny switches that are either 0 or 1, off or on, every piece of data. Numbers, text, images. This script is ultimately encoded in bits as a string of zeros and the ones. Classical bits are binary and mutually exclusive. At any given moment, a bit has a definite value, either 0 or 1. Dot. Never both. Now enter the qubit. Quantum bit. A qubit is the fundamental unit of quantum information, analogous to a bit in classical computing, but it leverages the quantum property of superposition. A qubit can be in state 0, state 1, or any superposition of 0 and 1 at the same time. In other words, whereas a classical bit is like a switch firmly flipped one way or the other, a qubit is like a switch that can hover in a combination of positions, partly 0, partly 1 until we check it. To make that more concrete, imagine a classical bit as a coin lying flat on a table, showing either heads, representing 1, or tails, 0, face up. A qubit is like a coin spinning in the air. While spinning, it's not just heads or tails, it's in a sort of limbo of both. Only when it lands, measurement, do we get a definite heads or tails outcome. But crucially, while spinning, the coin qubit contains information about both possibilities. WP is a testing psi with alpha plus beta squared equals 1. This normalization ensures the probabilities sum to 1. These alpha and beta are complex numbers that encode the probability of the qubit collapsing to 0 or 1 if measured. In fact, we can represent a qubit state by two numbers, amplitudes, alpha and beta, corresponding to the 0 and 1 states. For example, So a qubit might be 70% 0 and 30% 1, in a certain sense, until observed. Another helpful analogy: think of a sphere, the so-called Bloch sphere used to visualize qubits. A classical bit can only live at the North Pole, 0, or South Pole, 1, of the sphere. A qubit, however, can be at any point on the sphere's surface, meaning it has a much richer set of possible states, infinitely many superpositions of 0 and 1. Only when measured in the computational basis do we see either the North or South Pole outcome. But prior to that, it was at some superposition angle on the sphere. To put it simply, a classical bit is binary, 1 or 0. A qubit is quantum. It can be 1, 0, or both at the same time. This property alone is groundbreaking. Why? Because it allows a form of parallelism in computation. If you have two classical bits, they can be in only one of four possible configurations at a time: 0, 0, 0, 1, 10, or 11. Two qubits, however, can be in a superposition of all four of those configurations simultaneously. In general, n classical bits have one specific value out of 2 to the power of n possibilities at any moment, whereas n qubits can simultaneously represent all 2 to the power of n possible combinations in superposition. For example, 10 qubits can simultaneously represent 2 to the power of 10 equals 1024 different states at once. By the time you have 300 qubits, they can in principle represent 2 to the power of 300 states at once, which is a number larger than the number of atoms in the observable universe. This exponential capacity is what gives quantum computers their theoretical oomph. It's like having an enormously parallel computer, but not in the classical sense of separate parallel processors. Instead, the parallelism comes from superposition of states. It's important to clarify a common misconception. People sometimes say a qubit is both 0 and 1. So quantum computers try both answers of a computation at the same time. That's a heuristic, but not the full story. Simply being in superposition doesn't automatically give an answer to an arbitrary problem. The trick is in the quantum algorithm and how it uses interference. But it's true that with entangled qubits, a quantum computer can explore a vast computational space in a fundamentally different way than a classical computer. Thank you. Which must try possibilities one by one or on many parallel processors. To harness qubits, we also need entanglement. Qubits aren't just isolated. They can be entangled with each other, meaning their states become correlated in those spooky ways we discussed. Entanglement among qubits is what allows quantum computers to do computations that aren't just trivial parallel checks, but truly quantum operations where multiple possibilities interfere to amplify correct answers and cancel out wrong ones. More on that in a moment. Without entanglement, a quantum computer would be no more powerful than a classical one. This is a known result in quantum computing theory. Entanglement is a resource that provides a quantum advantage. Let's ground this in a simple example. A classical 2-bit register can hold one of four values at a time, say 1, 0. A 2-qubit register could be in a superposition like RENC, REN, 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 and REN positive 2, representing all four equally. If you have a function you want to evaluate on all four inputs, a classical computer must evaluate it on each input one by one, or with 4 separate processors. A quantum computer can, in one step, perform an operation on a superposition of all inputs. The result will be a superposition of all outputs. With clever algorithm design like Grover's search or Shor's factoring algorithm, you arrange for the outputs to interfere such that the correct answer is more likely to be observed. This is profoundly non-classical. It's why quantum computing is often likened to massive parallel computation in a single machine. Though the analogy isn't perfect, because reading out the result still yields a single outcome. You have to structure the computation such that the outcome you want is obtained with high probability. To sum up this part, bits are the currency of classical information: definite, binary, and independent. Qubits are the currency of quantum information: fluid, superposed, and capable of deep correlations, entanglement. Qubits leverage the core quantum phenomena we talked about. They superpose like Schrödinger's hypothetical cat, both 0 and 1. And multiple qubits entangle like Einstein's spooky pairs to act in concert. This gives quantum computers an extraordinary potential advantage. An analogy often used: think of a classical bit as a light switch that can only be up or down. A qubit is like a dimmer switch on a spinning dial. It can be at any angle between up and down, representing a continuum of combinations. But only when you check do you get a definite on-off. The magic is what you can do before you check. You can orchestrate a quantum computational dance that mixes and entangles these qubits and exploits interference. B. How quantum computers work. Conceptual. How do you actually compute with qubits? Obviously, it's not as simple as just loading a problem into a superposition and hoping the answer pops out. You need quantum logic gates and algorithms, analogous to logic gates and or not in classical circuits, that manipulate qubits in a controlled way, all while preserving their quantum coherence, their delicate superposition state. At a conceptual level, a quantum computer operates by initializing qubits, often to 0 states, and applying a sequence of quantum gates, which are reversible unitary transformations, like rotations on the Bloch sphere or entangling operations between qubits. These gates put qubits into superpositions, entangle them, and perform interference between probability amplitudes of different states. Finally, one measures the qubits, collapsing them to classical bits that hopefully encode the answer to the problem. The power comes from designing the gate sequence, the algorithm, such that out of the many superposed possibilities, the wrong answers cancel each other, and the right answer remains with high probability. This is done via quantum interference, analogous to how waves can cancel or reinforce each other. A well-designed quantum algorithm is like an orchestrated series of interactions that cause destructive interference for all the computational paths, leading to incorrect answers, and constructive interference for the paths leading to the correct answer. The result is that when you measure, you're very likely to see the correct answer, and you can amplify the success probability arbitrarily close to 1 by repeating and using majority vote, etc. if needed. One famous example is Grover's algorithm for searching an unsorted database. If you have n items and one marked item, a classical search takes on average n times 2 queries, in worst case n, to find the marked one. Grover's quantum algorithm finds it in about square root of n steps, a quadratic speedup. It treats the list as a superposition of indices, uses an oracle to flip the phase of the solution state, and then does an interference, Grover iterate, that amplifies the amplitude of the correct state. The interference phenomenon is key. After approximately square root n repetitions, the amplitude of the correct answer is near 1, and measuring yields that answer with high probability. Shor's algorithm for factoring, which made quantum computing famous in 1994, uses a quantum Fourier transform to find the period of a certain function. Leveraging superposition of many integers powers mod n, it offers exponential speedup over the best-known classical factoring algorithm, allowing a quantum computer to factor large numbers and thereby break RSA encryption exponentially faster than a classical computer. The details are complex, but at heart, it's using the fact that a quantum system can examine many possible factors at once and use interference to zero in on the correct one. From a hardware perspective, how do we implement qubits and gates? This is extremely challenging because qubits must maintain quantum coherence, isolation from environment noise, while also being controllable. There are several approaches. Superconducting qubits. These are used by IBM, Google, and others. They are tiny superconducting circuits, Josephson junctions, that have two energy states acting as 0 and 1. They are kept at extremely low temperatures, millikelvin, in dilution refrigerators to eliminate thermal noise. Microwave pulses are used to manipulate them, rotate their state, entangle pairs via coupling. Superconducting qubits operate fast, gates in tens of nanoseconds, but they can decohere in microseconds to milliseconds. So error correction is needed. Trapped ion qubits. Companies like IonQ and academic labs use individual ions, like Yb plus or Ca plus, trapped in electromagnetic fields in a vacuum. The ion's internal electronic states, or collective vibrational modes, serve as qubits. Trapped ions have very long coherence times, seconds or more, and high-fidelity gates. But gates are slower, microsecond to millisecond range, and scaling to many ions is challenging due to controlling many laser beams and modes. Lasers manipulate their states and entangle ions by causing them to interact via Coulomb forces. Photonic qubits. Using photons, particles of light, as qubits, usually with polarization or path encoding the 0 and 1. Photons are great because they travel fast and hardly interact with environment, so low decoherence. But that makes entangling them directly tricky. Photonic quantum computing often uses beam splitters, phase shifters, and single photon sources and detectors, plus often some form of measurement-based quantum computing, one-time use entangled states, or nonlinear materials for interaction. It's promising for quantum communication, since photons naturally carry info in fibers or free space. Spin qubits in semiconductors. These use the spin of single electrons in quantum dots or impurities in solids, like silicon or diamond vacancies. They can leverage the semiconductor industry's fabrication know-how. For instance, silicon spin qubits, like at Delft or Intel, use single electron spins in tiny silicon transistor-like structures. They have long coherence, if isolated, and can be scaled in principle on chips. But controlling and entangling them, via exchange interactions or microwave control, is complex. NV centers in diamond, nitrogen vacancy defects, offer a solid-state qubit that can even function at room temperature with certain trade-offs. Topological qubits A more exotic approach, pioneered by Microsoft's research efforts, aims to use quasi-particles called Majorana zero modes in certain superconducting nanostructures. These promise qubits that are inherently protected from certain errors via topological properties. However, these are still in experimental stages. Evidence of Majorana modes has been claimed and debated. A lot of R&D remains until topological qubits become usable, if ever. Regardless of approach, all quantum computing hardware faces common challenges. Decoherence, qubits losing their quantum state due to interaction with environment. Noise and errors in gates. Difficulty of scaling to large numbers of qubits while maintaining controllability and low error rates. Quantum states are fragile. Any stray interaction, like a stray magnetic field, a cosmic ray, lattice vibration, etc., can collapse a qubit state. So qubits need isolation, often extreme conditions like ultra-low temperature vacuum setups. Yet they also need to be coupled to each other and to control readout devices when we perform operations or measure. It's a delicate balancing act. In a functional quantum computer, operations are performed by analogs of logic gates. For example, a Hadamard gate puts a single qubit into equal superposition of 0 and 1, a quantum coin flip. A Pauli X gate is like a quantum knot, flips 0 into 1, etc. There are also two-qubit gates like the C knot, controlled knot, which entangles qubits, flips second qubit if the first qubit is 1. Programming a quantum computer means specifying a sequence of these quantum gates, often described in circuit diagrams or coded in languages like Q# or Qiskit, to achieve a certain transformation on an initial state and then measuring the result. With a universal set of such gates, one can compose any quantum algorithm, just as classical gates compose classical circuits. Another aspect, because of the probabilistic nature of quantum measurement, quantum algorithms often need to be run multiple times and a distribution of outcomes collected to confidently extract the answer. For example, Shor's algorithm will output the correct factor with high probability, but you might run it a few times to be sure, since there's a chance of a dud result. This is analogous to how a Las Vegas algorithm in classical computing might occasionally fail but usually succeed with probability greater than 1/2.
And you amplify success by repetition. One of the hardest parts of making quantum computing practical is dealing with errors. Unlike classical bits, which can be copied and have straightforward error correction, like parity bits,
Checksums, qubits can't be naively copied, the no-cloning theorem, and errors are analog in nature. But researchers have invented clever schemes for quantum error correction by entangling multiple physical qubits to represent one logical qubit, here, and spreading information across them via specific quantum codes. The system can detect and correct certain errors without measuring the actual information, thus avoiding collapse. For example, the surface code is a leading quantum error correction code that might require on the order of 100 physical qubits per logical qubit to get error rates low enough for large algorithms. Error correction is possible, but it dramatically increases the number of qubits needed. This is why current devices with tens or hundreds of qubits can't do long computations without errors. We don't yet have enough qubits overhead to fully error correct them. We are in what's called the NIST era, noisy intermediate scale quantum, meaning we have small quantum processors that are not error-corrected and still prone to noise. They can do some demonstrations and small algorithms, but they're not powerful enough for big practical tasks yet. Despite these challenges, engineers have made astonishing progress. In 2019, Google's 53-qubit superconducting chip Sycamore performed a specialized task, random circuit sampling, in about 200 seconds, which they estimated would take the fastest supercomputer thousands of years, an achievement they termed quantum supremacy. IBM contested the exact comparison, claiming their supercomputer could do it in a shorter time than that. But nonetheless, it was a milestone showing a quantum device outperforming classical for a contrived problem. IBM has been steadily increasing qubit counts. They had 127 qubit devices, Eagle processor, by 2021, and have announced a 433-qubit Osprey in 2022, and aim for over 1,000 qubits, Condor, soon. On the road to a million-qubit future, trapped ion systems have shown very high-fidelity gates and entangled dozens of ions. Different approaches have different strengths. It's not yet clear which will become dominant. Possibly a combination of technologies will coexist for different uses, like superconducting for fast computation, photonic for communication links, etc. So conceptually, how a quantum computer works is initialization. Prepare all qubits in a known state, often 0 to 0. Quantum circuit computation. Apply a sequence of quantum gates, unitary operations that entangle and evolve the qubits according to the algorithm. During this, the system must be largely isolated so it evolves under gate control and not environmental decoherence. The gates themselves are implemented via controlled pulses, microwave pulses for superconducting. Stop sudden things. Laser pulses for ions, etc., that affect transitions or phase shifts as desired. Measurement. At the end, measure the qubits. The wave function collapses and you obtain a string of classical bits, e.g., dot. A measurement of each qubit gives 0 or 1. The outcome is the result of the computation, often requiring some interpretation or repeated runs. The trick of algorithm design is to get a high likelihood that those measured bits encode the correct answer. This often involves clever use of interference. If you recall our discussion of double slit, certain paths canceled and others added. In a quantum algorithm, computational paths can interfere. You want wrong answers to destructively interfere, and right answers to constructively interfere. Achieving that is not trivial. It took geniuses like Shor to find an algorithm for factoring, and many problems still don't have known efficient quantum algorithms. Quantum computers are not magic bullets for all problems. For many tasks, a classical computer is just as good or even better for now. They won't replace classical computers for everything. Rather, they'll be like specialized coprocessors for certain hard problems. It's known, for example, that quantum computers speed up factorization, Shor's algorithm, and unstructured search, Grover's algorithm, gives quadratic speedup. And they exactly solve certain quantum, physics/chemistry simulations exponentially faster, since they natively handle quantum state complexity. But for some problems like basic arithmetic or database transactions, classical computers will remain very efficient. So it's not a universal speed-up device, But for some impactful domains, the speedups are enormous. What quantum computers will do? Applications. So where are the killer apps of quantum computing? Why are governments and companies investing billions in this tech? Let's explore a few major application areas where quantum computers, once sufficiently advanced, could be game changers. Drug discovery and materials science. One of the most natural applications of quantum computers is simulating quantum systems themselves, such as molecules and materials. Richard Feynman originally proposed the idea of a quantum computer in 1981, precisely because simulating even modest-sized molecules on classical computers is incredibly hard. The computational resources grow exponentially with the number of particles. But a quantum computer can natively represent the quantum states of a molecule. This means we could simulate chemical reactions, protein folding, or material properties with high accuracy without needing exponential resources. The impact is huge. We might design new medicines by simulating how a drug molecule interacts with a target protein, finding effective shapes and binding energies in silico rather than through costly trial-and-error lab experiments. We might discover new materials with desirable properties, for example, superconductors that work at room temperature, revolutionizing energy transmission, or better catalysts for industrial processes. As a notable example, the process for making fertilizer, the Haber-Bosch process to fix nitrogen, consumes a couple percent of global energy. Bacteria do it efficiently with an enzyme whose complex quantum chemistry we struggle to simulate. A quantum computer could help design a better catalyst by understanding that chemistry, potentially saving huge energy. Quantum simulations could also help in creating more efficient batteries by analyzing materials at the atomic level, or new solar cell materials, etc. Essentially, any domain where understanding and designing molecules or materials is key, quantum computing could accelerate discovery. In the pharmaceutical industry, a major challenge is that many drug candidates fail in trials because we can't perfectly predict their interactions. Quantum computing might allow in silico testing of drug binding and reactivity with unparalleled accuracy. This could bring life-saving drugs to market faster and cheaper. Similarly, designing lightweight but strong materials or novel electronics, like topological insulators for next-gen chips, often requires understanding quantum behavior of electrons in solids. Quantum computing could handle models that defeat classical methods. Optimization problems. Many problems in logistics, finance, and engineering come down to finding an optimal arrangement or solution among exponentially many possibilities.
Examples include routing airplanes efficiently, optimizing supply chain delivery, scheduling factory machines, portfolio optimization in finance, or even optimizing machine learning hyperparameters. Classical algorithms struggle with large instances of these.
They might be NP-hard or just combinatorially explosive. Quantum computers offer some potential advantages here. One avenue is using Grover's algorithm or variance for searching solution spaces faster than classical, a quadratic speedup. Another is the use of quantum annealers or the quantum approximate optimization algorithm, QAOA, to find good solutions for combinatorial optimization problems. While it's not proven that quantum computers will exponentially speed up all optimization tasks, likely not in general, so They could significantly reduce time for many practical cases. For example, imagine an airline wants to schedule thousands of flights with minimal delays and fuel usage. That's a huge optimization. A quantum computer might explore many schedule configurations in superposition and bias towards the optimal one more efficiently than brute force. Or consider traffic light optimization in a city. Controlling dozens of lights to minimize jams is complex. Quantum algorithms might help find timing patterns that significantly reduce congestion. In finance, selecting an investment portfolio to maximize return and minimize risk, Markowitz optimization, often requires evaluating many combinations. Quantum computers might handle the heavy lifting of that computational problem faster. It's worth noting companies like Volkswagen and BMW have already dabbled in quantum algorithms for traffic flow optimization and factory scheduling, using early quantum processors or simulators, hinting at the interest in this area. Even if the speedups are moderate, when applied to huge logistical networks, the savings in time and cost could be enormous. Cryptography and security. This is a double-edged sword. Quantum computers threaten certain existing encryption methods, but also offer new secure communication methods. Let's start with the threat. Cryptography today relies heavily on mathematical problems that are believed to be hard for classical computers. For instance, RSA encryption, widely used for secure websites, banking, etc., relies on the difficulty of factoring large numbers. A 2048-bit RSA key's strength comes from the fact that factoring a approximately 600-digit number is beyond any classical capability. However, Shor's algorithm on a sufficiently large quantum computer could factor such numbers exponentially faster. Breaking RSA and related schemes, like elliptic curve cryptography, via a similar algorithm. In essence, a powerful quantum computer could render most of today's public key cryptography insecure. It could decrypt secure communications, forge digital signatures, etc. This is a major impetus. Agencies like NIST have been standardizing new cryptographic algorithms for exactly this reason. Some estimate we might need to be quantum safe by the 2030s if quantum computing progresses. The specter of encrypted data being recorded now and held until decrypted later by a quantum machine. A harvest now, decrypt later attack is driving urgency in this migration. So quantum computing is like the ultimate code breaker for certain codes. Not all cryptography is broken by quantum. Symmetric ciphers like AES are only mildly affected. Grover's algorithm can brute force keys in square root of n time, meaning you double the key length to regain security, so those remain safe with modifications. But public key systems, RSA, Diffie-Hellman, ECC, are vulnerable to Shor's algorithm. On the flip side, we have policies to work with. Quantum physics also enables new unbreakable encryption methods through quantum communication and quantum key distribution, QKD, which we'll discuss more in the next section, using entangled photons or other means, and said. Two parties can share encryption keys with security guaranteed by the laws of physics. Any eavesdropping attempt on the quantum channel will disturb the state and be noticed. This is already being deployed in niche applications, banks, government communications. So, As quantum computers arise, we'll likely shift to a mix of quantum-resistant classical algorithms and possibly quantum-based secure channels for the highest security needs. But back to quantum computing uses, aside from code breaking, a quantum computer could help improve security in other ways, like generating truly random numbers, important for cryptography, using inherent quantum randomness, or possibly solving certain verification problems faster. However, the headline is indeed that quantum computers will break certain current crypto systems. This is sometimes dramatized as the Y2Q moment, year to quantum, a potential future point where if you haven't updated your security, an adversary with a quantum computer could wreak havoc. It's a powerful example of how quantum physics, which started as abstruse theory, directly impacts global cybersecurity, artificial intelligence, and machine learning. This is a newer and evolving area, but many researchers are exploring how quantum computers could accelerate machine learning tasks. There are a few angles. One is using quantum computers to speed up linear algebra computations, which underlie many ML algorithms, like solving systems of equations, inverting matrices, doing Fourier transforms. There's an algorithm called HHL, Haro-Hasidim-Lloyd, for solving certain linear systems exponentially faster, which could hypothetically speed up things like regression or classification that involve large matrix operations. Though it has caveats about the data being in a quantum form, other approaches include quantum neural networks, using qubits and quantum gates to mimic the processing of a neural network, potentially compressing large networks into fewer qubits by leveraging high-dimensional quantum states. There's also interest in using quantum computers for faster combinatorial optimization, which appears in NL, examples in training certain models or feature selection. Quantum-enhanced machine learning might for example, classify data in a higher dimensional Hilbert space more naturally than a classical algorithm could, similar in spirit to kernel methods, but using quantum states. It's still uncertain exactly which ML tasks will see the biggest quantum boosts. But some promising areas are quantum support vector machines, quantum recommendation systems, like an algorithm by Karanides and Prakash for recommendation problems that had exponential speedup under certain conditions, and accelerating certain clustering or sampling tasks. Additionally, machine learning might help calibrate and correct quantum devices in real time, an interplay of AI helping quantum and vice versa. It's fair to say quantum computers won't magically make any AI problem trivial, but they could provide boosts for data analysis and optimization aspects of AI. For instance, imagine being able to search huge solution spaces of model parameters or network architectures faster via Grover-like search, or performing massive parallel processing on quantum states that encode data, potentially revealing patterns faster. One concrete example: Google researchers and others have explored using quantum circuits as a sort of generative model, quantum circuit-born machine, to capture probability distributions of data. Akin to how classical generative models work, but tapping into quantum probabilities. Time will tell how significant these quantum advantages in AI will be. But given how central AI and big data are, even modest speedups could be valuable. If a quantum computer could, say, cut training time of a complex model from weeks to days, that's a big deal in fields like drug discovery or climate modeling that rely on machine learning. Now let's take a step back from specific fields and consider the current landscape of quantum computing and its challenges. The current landscape and challenges. We are in the early stages of the quantum computing revolution, often referred to as the NISQ era. Noisy intermediate scale quantum means our current quantum processors still have significant error rates and short coherence times. Intermediate scale means tens to a few hundred qubits. Not yet the millions likely needed for full-scale, error-corrected algorithms like factoring big numbers. It's analogous to the 1940s or 1950s in classical computing when vacuum tube computers existed. They could do calculations, but were prone to errors and limited in size. Yet they proved the concept and spurred development of better technology. Major players are investing heavily. IBM has an active roadmap. Stop. Google's quantum AI division achieved the aforementioned quantum supremacy experiment in 2019 with a superconducting chip, and is now focusing on scaling and error correction. They recently demonstrated quantum error correction, forming a logical qubit with modest error suppression, providing cloud access to quantum processors with increasing qubit counts, from 5-qubit chips a few years ago to 127-qubit and soon larger, and has demonstrated complex circuits. Companies like IonQ and Quantinuum, formed from Honeywell's quantum division and Cambridge Quantum, are advancing trapped ion systems, which have fewer qubits, dozens, but very high-fidelity operations. There are also many startups exploring different technologies. Rigetti, superconducting, PsiQuantum, photonic aiming for a 1,000,000-qubit photonic machine using silicon photonics. D-Wave, quantum annealing devices with thousands of qubits, which are a different model of computation specialized for certain optimization problems. Governments across the world, US, EU, China, etc., have initiated large quantum research programs, seeing both the economic potential and the national security implications, like cryptography. It's a bit of a global space race for the next computing frontier. However, significant challenges remain before we have truly transformative quantum computers. Error rates and decoherence. Current qubits are imperfect. A superconducting qubit might maintain coherence for, say, 100 microseconds and have a 2-qubit gate fidelity of perhaps 99.5%. That sounds high, but when you need thousands of operations, those errors compound. Quantum error correction requires gate error rates on the order of 0.1% or 0.01% or lower, plus a large overhead of physical qubits to correct one logical qubit. We're actively researching ways to improve fidelities, like better materials, isolation, noise mitigation techniques, and to demonstrate error correction actually extending logical qubit lifetimes. Some progress is being made. For example, distance 3 surface code tests. Scaling up qubit count. Superconducting circuits can be lithographically fabricated, so in principle, integrating hundreds or thousands on a chip is feasible. But control wiring and crosstalk become issues. The chips have to be connected to classical electronics at room temperature with lots of coax lines. Different platforms face different scaling issues. The fridge becomes a wiring jungle. Also, each added qubit adds potential noise sources unless carefully managed. Trapped ions can in principle chain many ions, but too many and the modes get hard to manage. Or one might connect multiple ion traps via photonic links. Photonic qubits need reliable single-photon sources and detectors, and maybe quantum memories to be scalable. Spin qubits have the appeal of leveraging semiconductor fab, but controlling each spin and getting them to interact in a large 2D array is non-trivial. Every approach sees a long engineering path from small demo systems to millions of qubits. IBM's plan, for instance, involves modular chip architecture, connecting multiple chips via quantum interconnects to reach larger qubit numbers. Software and algorithms. While hardware is being built, we also need software, compilers, error mitigation techniques, new algorithms that are practical on nearer-term devices. The famous algorithms, Shor, Takenberg, Grover are great, but require thousands of perfect qubits to do something like break RSA 2048, which might be years away. In the interim, researchers are exploring hybrid algorithms, variational quantum algorithms, that use a quantum computer as a subroutine and a classical computer in loop to solve problems. Examples include VQE, Variational Quantum Eigensolver for Chemistry, or QAOA for optimization. These might deliver value even with noisy qubits by finding better solutions than classical alone for certain tasks. The field of quantum software is in its infancy, analogous to classical computing before people discovered all the useful classical algorithms. We likely haven't yet discovered all the potential killer quantum algorithms. More will emerge as more brains get to play with actual quantum machines, and as theoretical understanding improves. There's active research in finding new algorithms for machine learning, differential equations, even verification tasks. Despite the challenges, the progress is steady. It feels reminiscent of early days of flight. We've gotten a few feet off the ground with rickety contraptions. Robust jetliners are still some ways off. But the basic possibility is proven. As one metric, in 1998, the first 2-qubit quantum logic gate was demonstrated in an ion trap. By 2023, we have machines with 50 to 100 qubits performing small algorithms and even small instances of error correction. There's even a distributed quantum internet in the works, efforts to entangle distant nodes via photons, which would allow secure communications and distributed quantum computing. In 2021, researchers demonstrated a rudimentary 3-node quantum network where entanglement was swapped between nodes. Baby steps toward a future quantum internet that might complement our classical one, providing secure communication channels via QKD and linking quantum processors in different locations. It's truly an exciting time. Leading companies, IBM, Google, Intel, Microsoft, Amazon, etc., and many startups are pouring resources into this. It's not purely hype either. While some timelines are overly optimistic in media, the core science is solid and incremental progress is measurable. For perspective, IBM aims to have perhaps greater than 1,000 qubits by 2024 and begin implementing error correction beyond that. Google has a roadmap for a useful error-corrected quantum machine within a decade. No guarantees, but significant momentum. Many universities and national labs are also involved, pushing the boundaries of materials, designs, and novel qubit types, like neutral atoms in optical tweezers, a promising new approach. E.g., Pascal's startup arranges atoms with lasers to act as qubits, making entangling gates via Rydberg interactions. Those systems have hit 100-plus atom qubits too in analog computing mode. The ecosystem is rich. In summary, we stand on the threshold. Small quantum computers exist and can do specific tasks faster or differently than classical ones as a proof of principle. But they are not yet at a scale to transform mainstream computing. The challenges are tough, but each year brings new records in qubit count and fidelity. The hope is that within a decade or two, we'll have medium-sized quantum computers that can, for example, accurately simulate moderately complex molecules, enabling chemists to design new drugs or solve optimization problems far beyond current reach for industry. And beyond that, large-scale fault-tolerant machines that could handle code-breaking or huge scientific simulations. The quantum computing revolution is often likened to the early computer revolution. Back in the 1940s, people wondered if these huge, finicky machines would ever be practical. By the 1960s, we had mainframes. By 1980s, PCs. By 2000 smartphones. It's not unreasonable that quantum tech could follow a similar trajectory, from lab curiosities to indispensable tools, though perhaps with its own unique path. So, as you relax and take this in, realize you're living through what might be viewed historically as the dawn of a new age of technology, the quantum age. The basic science, the strange rules of quantum mechanics, took decades to accept and understand. Now, a few generations later, mere turning those weird rules into working devices. It's the ultimate vindication of the usefulness of useless knowledge as things learned about electron spins and photon polarization in thought experiments are now literally enabling new tech. Having focused heavily on quantum computing, let's not forget there are other applications of quantum science that are emerging too, in communication, sensing, and more. In the next section, we'll briefly tour some of those, how quantum mechanics is enabling secure communication and ultra-sensitive measurements, as well as new states of matter. After that, we'll step back and muse on the big philosophical questions about reality that quantum physics raises before concluding our journey. Take a deep breath. We've covered a lot of ground, from the basic quantum phenomena to their revolutionary application in computing. Let's continue at a gentle pace to see the broader picture of the quantum leaps happening beyond computing. Beyond computation, other quantum science applications. Quantum physics isn't only about computing. The same strange properties of quantum particles, superposition, entanglement, etc., can be harnessed in other domains too. In this section, we'll explore a few key areas: quantum communication and cryptography, quantum sensing and metrology, and quantum materials. These are often called part of the second quantum revolution as well. The first revolution gave us transistors and lasers. The second gives us technologies based on direct manipulation of quantum states. We'll see how entanglement can make communication ultra-secure, how quantum effects enable sensors of exquisite precision for imaging and navigation, and how understanding quantum materials could yield breakthroughs in energy and electronics. Quantum communication and cryptography. When we say quantum communication, we typically mean transmitting information in the form of quantum states, like photons that are in superposition or entangled with others. The prime application of this is quantum key distribution, KKD, a method to share encryption keys between two parties with security guaranteed by the laws of physics. The idea was first proposed in the 1980s, BB84 protocol by Bennett and Brassard, and has since been demonstrated in various forms. Even over satellite links. Here's how it works in simple terms. Imagine Alice and Bob want to share a secret key, a random string of bits, to later use for encrypted communication. They have a quantum channel, say, an optical fiber or free space link, and a classical channel, regular internet phone, which can be public but authenticated. Alice sends Bob a series of photons, each polarized in one of several possible bases. For instance, in BB84, Alice chooses randomly to send each photon polarized either rectilinearly, 0 degrees or 90 degrees, representing bits 0 or 1, or diagonally, 45 degrees or 135 degrees. Bob doesn't know which basis Alice chose for each photon. So he guesses a basis randomly for each one to measure the photon, rectilinear or diagonal. Because measuring in the wrong basis gives a random outcome, Bob's measurements will match Alice's sent bits only for the cases where he happened to choose the same basis Alice used. After the transmission, Bob tells Alice, over the classical channel, which photons he measured in which bases, but not the results. Alice tells Bob which bases were the correct ones for those photons, i.e., which ones they were aligned on. They discard all cases where the basis didn't match. The remaining cases, where Bob measured in the right basis, should theoretically give Bob the same bit Alice sent. These bits become their shared key. Now the genius is in the security. If an eavesdropper, Eve, tries to intercept the photons and measure them, she doesn't know the correct bases either. Any measurement she does will disturb the photons because quantum measurements irreversibly collapse states. So if Eve intercepts and resends photons, her presence induces errors in the key that Alice and Bob can detect. Specifically, after establishing the raw key, Alice and Bob publicly announce a subset of the bits, selected randomly, to check for consistency. If too many of these check bits differ, they know the line was compromised because an eavesdropper's measurements introduced errors. If the error rate is below a threshold, they can proceed, perhaps doing further error correction and privacy amplification to distill a final secret key. The principle is that observation disturbs the system. In QKD, any eavesdropping attempt will unavoidably leave a trace, a higher error rate. Thus, as long as Alice and Bob detect no significant eavesdropping, they have a key that is provably secure, even if an eavesdropper had unlimited computing power, classical or quantum. This is unlike current public key crypto, which relies on assumed mathematical difficulty. QKD is secure based on physics itself, so QKD offers truly unhackable communication channels for the encryption keys. Note, QKD doesn't transmit the message itself in quantum form usually. It's mostly used to share a one-time pad or encryption key, which is then used to encrypt the actual message sent over normal channels. Since one-time pads, random keys used only once, are theoretically unbreakable if the key is secret. Combining QKD with one-time pads yields communication that is information theoretically secure. Real-world implementations. Fiber-based QKD can work over distances of a few hundred kilometers. Loss in fiber eventually kills the signal. There are commercial QKD systems already used by some banks and government agencies for high-security links. For example, Quantum Leap. Geneva, Lausanne had a QKD link for some financial communications. In 2017, China launched the Haience satellite, which demonstrated QKD between ground stations 1,200 kilometers apart by beaming entangled photons down to 2 locations. They even held a secure video conference between Beijing and Vienna using keys exchanged via satellite QKD. This showed the feasibility of space-based quantum communication, effectively a rudimentary quantum network spanning continents. Recently, a team achieved a long-distance QKD between China and Italy by chaining satellite and fiber links. Countries are now planning for a quantum internet, a network of quantum repeaters and satellites to extend quantum entanglement distribution worldwide. The EU and US have programs for a quantum-secured network infrastructure in the coming decades. One slight caveat: QKD provides secure key exchange, but it doesn't address all of communications security. Also, practical QKD devices can have side-channel flaws, like a detector might be tricked by bright light, so-called blinding attacks, etc. However, with careful design, those can be closed. There's a push for device-independent QKD, which uses entanglement and Bell inequality tests to ensure security, even if the devices aren't trusted. A very quantum idea that if the outcomes violate Bell's inequality, no local classical eavesdropper could be spying. Beyond QKD, quantum communication includes the idea of quantum teleportation, not teleportation of matter, but of quantum states. Using entanglement and classical communication, one can transfer an unknown quantum state from one location to another without physically sending the particle that carried that state. This has been demonstrated between labs and even between a satellite and ground. It's a fundamental technique for future quantum networks to send qubit states around, important for distributed quantum computing or extending QKD via quantum repeaters. In summary, quantum communication promises communication channels fundamentally guarded by quantum physics. As long as quantum theory holds, no eavesdropper can steal the key undetected. This is particularly pertinent given the looming risk of quantum computers breaking current encryption. QKD is one solution to keep security strong in a post-quantum world. Governments are certainly interested. E.g., China has a quantum communication backbone between Beijing and Shanghai, 2,000 kilometers, with trusted nodes along the way, operational. And Europe is building the EuroQCI, a quantum communication infrastructure. For the average person, we might not see QKD in daily life anytime soon, since classical post-quantum cryptography might secure most consumer comms without needing new hardware. But for high-value targets, quantum communication could become the gold standard of secrecy. It's a great example of how entanglement's spooky action can be put to good use if someone tries to spy. The entanglement is disturbed, and you immediately know. Quantum sensing and metrology. Another less publicized but very impactful area is using quantum phenomena to build sensors and measurement devices that far surpass classical limits of precision. This field, quantum sensing metrology, takes advantage of things like superposition and entanglement to measure quantities, time, magnetic fields, acceleration, etc., with extremely high precision or sensitivity. Some key examples. Atomic clocks. These are arguably the most successful quantum sensors already. Atomic clocks use the quantum transition frequency of atoms, like cesium or rubidium, as the pendulum to keep time. Because atomic transitions between two hyperfine levels, for instance, are extremely stable and identical for all atoms of the same isotope, they provide an ultra-precise frequency standard. The current best atomic clocks, using strontium lattice clocks or ytterbium, etc., have accuracies on the order of losing less than 1 second in the age of the universe. That's how we define the second nowadays, by a cesium atom's frequency. These clocks are essential for GPS. The timing accuracy of satellites' clocks directly affects position accuracy. Telecommunications and fundamental science. Quantum mechanics underpins them. The idea that an atom will absorb emits photons of a very specific frequency corresponding to an energy difference. By locking a laser to that frequency via feedback, you get a stable clock. Researchers even use entangled atoms or squeezed states to try to go beyond the standard quantum limit in clocks, hoping to further increase timing precision. Better clocks not only make GPS more accurate, but enable tests of general relativity, like detecting tiny gravitational potential differences between heights via time dilation's effect on clocks, and potentially help in navigation if GPS fails, inertial navigation using precise time. Magnetometers, using quantum effects to measure magnetic fields at extremely small levels. One popular sensor uses NV centers in diamond, a defect where a nitrogen atom replaces a carbon next to a vacancy, which has quantum spin states sensitive to magnetic fields. By monitoring the spin resonance of NV centers, which shifts with magnetic field, you can detect fields as faint as those produced by neural activity in the brain or by geological formations. Such quantum magnetometers are used in biomedical imaging, like MEG, magnetoencephalography, to map brain activity by its magnetic signals, potentially improved with NV diamond sensors. They're also useful in sensing for mineral exploration or detecting unexploded ordnance by tiny magnetic signatures. Another example, SQUIDs, superconducting quantum interference devices, are extremely sensitive magnetometers relying on quantum interference of superconducting electron pairs. They can measure magnetic fields in the femtotesla range, incredibly small. Those are used in medical imaging, like to detect the faint magnetic fields of the heart or brain, and in physics experiments. Gravimeters and accelerometers. These measure gravitational or inertial forces. Quantum versions often use atom interferometry. You toss up atoms and split their matter waves. Let them follow different paths in a gravitational field, then recombine them. The interference pattern tells you about the acceleration, gravity, they experienced. This can measure local gravitational acceleration so precisely you can detect underground structures like voids, water, or ore deposits because they slightly change the local gravity. These quantum gravimeters and accelerometers can serve as extremely accurate navigation aids, like a very precise IMU, inertial measurement unit. If GPS is denied, say a submarine underwater or in military scenarios, an onboard quantum accelerometer could track position by dead reckoning with minimal drift. In 2018, DOT, a portable atomic interferometer gravimeter, was demonstrated in the UK that could measure gravity and detect a tunnel underground purely by the gravitational anomaly. Quantum imaging. There are quantum techniques like using entangled photons to go beyond classical resolution limits or to image with lower light intensity. For instance, quantum illumination uses entangled light to detect objects in noisy backgrounds more effectively than classical light. Also, sensors like the one mentioned for MRI, there's research on using quantum sensors like NV centers again to detect single proton spins, which could eventually lead to MRI that can image individual molecules, a sort of quantum MRI concept. Already, NV diamond probes have imaged single electron spins and small clusters of nuclear spins, which is something classical MRI could never do. Its bulk. This might revolutionize fields like structural biology by directly imaging the magnetic fields from molecular structures. Precision metrology experiments. Quantum sensors allow tests of fundamental physics. Example, LIGO, the gravitational wave detector, uses quantum squeezed light to enhance its sensitivity beyond the shot noise limit of lasers. LIGO injects squeezed states of light, a quantum optical state with reduced noise in one quadrature, to improve the interference measurement of spacetime ripples. This was crucial in improving sensitivity to actually detect gravitational waves from distant black holes merging. So quantum optics helped enable an entirely new astronomy. Another ambitious application, searching for elusive dark matter candidates or measuring potential tiny violations of known physics. Quantum sensors, like ultra-cold atom clocks or resonators, can look for tiny changes that would indicate new physics. For example, experiments with atomic clocks set limits on time variation of fundamental constants. To illustrate how sensitive quantum sensors have gotten, scientists have detected the subtle effect of Earth's gravity on time dilation by comparing two atomic clocks with a height difference of just 1 foot. And a recent proposal uses entangled clock networks to detect passing gravitational waves or dark matter fields. The higher clock ticked a bit faster as predicted by relativity. This was done with optical lattice clocks. That's measuring gravitational potential differences on a very human scale. Essentially, a new way to see height differences by time. Quantum sensing is a bit behind computing in public visibility, but likely to mature faster in practical deployment, since many sensors don't require millions of qubits. Just clever use of a moderate number of quantum systems, or even single atom effects. We already use atomic clocks daily, GPS. The navigation angle is interesting. A quantum inertial navigator combining atom interferometers could allow a submarine to navigate precisely for long periods without surfacing, whereas classical inertial nav drifts too much over time. Soon, quantum gyroscopes might appear in aircraft or ships for navigation. That's of military interest. Also, quantum magnetometers could aid in submarine detection or in mineral exploration. Medical imaging. Quantum sensors might lead to ultra-sensitive magnetoencephalography that doesn't need expensive shielding or cryogenics. Making something like a wearable brain scanner possible by using optically pumped magnetometers or NV diamond sensors at room temperature. This could revolutionize neuroscience or brain-computer interfaces by providing high-res, real-time brain activity maps. There's also work on quantum-enhanced MRI that could improve signal-to-noise, meaning sharper images with lower scan times. To generalize, quantum sensing often exploits entanglement or squeezing to beat classical noise limits. For example, if you have n atoms sensing a field classically, not entangled, your precision improves as the square root of n, standard quantum limit. But if those atoms are entangled in a specific way, a squeezed or GHZ state, you could improve as n, Heisenberg limit, which is a huge gain for large n. This has been shown in lab for small atom ensembles and used to slightly improve atomic clock performance. Quantum sensors can act as superpowered eyes and ears in environments, detecting tiny changes in fields, forces, temperatures, etc. For instance, the first direct detection of nuclear magnetic resonance (NMR) signals from a single protein was achieved with a quantum sensor NV center, something impossible with standard NMR, which needs trillions of identical molecules. This points toward single molecule NMR or MRI, which could let us determine structures of molecules without needing to crystallize them, circumventing a big step in X-ray crystallography. Another example, gravitational wave detectors in the future might use entangled masses or improved squeezing to catch even fainter waves or higher frequencies, or detecting the Earth's rotation precisely with atom interferometers as a gyroscope, useful for geodesy or tests of general relativity, the equivalence principle, frame dragging, etc. Overall, quantum sensing applies quantum tricks to measure things extremely well. It's a quieter revolution, but one likely to yield benefits in many areas, making GPS independent through onboard clocks accelerometers, improving medical diagnostics, aiding fundamental science, and giving industry new measurement capabilities. For example, detecting stress or cracks in materials via quantum sensors or monitoring tiny magnetic signatures in chip fabrication for better quality control. As these sensors become more practical outside labs, some are already commercial in niche markets, like compact atomic gravimeters for surveying or small atomic clocks for telecom networks. They'll start to have real-world impact. Imagine going to a hospital that can perform a brain scan with you just wearing a quantum sensor cap. No giant MRI magnet needed. That could allow continuous brain monitoring or much more accessible neural imaging. Quantum sensors often piggyback on advancements from atomic physics and quantum optics research. For instance, lasers to cool and trap atoms were originally fundamental research. Now they're part of these devices. Similarly, the development of reliable single-photon detectors helped both quantum comms and sensing. In conclusion, for sensing, quantum tech will sharpen our senses, giving us microscopes that see single atoms, clocks that don't miss a beat in billions of years, and instruments that detect the faintest whispers of the environment. They are extensions of human measurement ability, riding on quantum phenomena. Quantum materials. The term quantum materials refers to materials where quantum effects, beyond just basic chemistry, lead to novel behaviors. Often new phases of matter with exotic properties. This includes things like high-temperature superconductors, graphene, and other 2D materials, topological insulators, quantum magnets, etc. While developing materials has always involved quantum physics, since bonding and electrons are quantum, the field of quantum materials deliberately seeks or studies materials where collective quantum phenomena, entanglement, topology, quantum fluctuations result in useful properties. By understanding these ... we can potentially engineer new technology. Some highlights: superconductors. These are materials that conduct electricity with zero resistance below a certain critical temperature. Traditional superconductors work at very low temperatures, near absolute zero. But so-called high-TC superconductors, often copper oxide ceramics discovered in the 1980s, work at up to approximately -140 degrees Celsius, still cold, but higher than old ones. The mechanism is complex and involves quantum pairing of electrons, Cooper pairs, via lattice vibrations. Superconductors are quantum because they exhibit a macroscopic quantum state. Electrons form a condensate, described by a single wave function across the material. This leads to phenomena like the Meissner effect, magnetic fields expelled, and quantized vortices. If we could find or design a room-temperature superconductor, it would change the world. Lossless power grids, maglev trains widespread, ultra-efficient motors, and MRI machines without expensive cooling, etc. So a lot of quantum materials research tries to understand superconductivity and find new superconductors. Recently, hydrogen-rich materials under high pressure achieved near-room temp superconductivity, but impractical due to required pressure. Still, it's progress. Even incremental improvements in superconductors can save enormous energy. Currently, cooling for superconducting magnets or wires is a big overhead. Topological insulators and topological superconductors, these are materials that have a very interesting quantum property. They insulate in the bulk, but have conducting surface or edge states that are protected by the material's topology, essentially robust against defects. If operating temperatures get higher, cooling gets easier. This arises from strong spin-orbit coupling and band structure topological invariance. Why are they exciting? The surface states in a topological insulator have electrons with spin locked to their direction of motion, and they resist backscattering. This could be useful for low-power electronics or spintronics, using electron spin for information. Topological superconductors are sought because they might host Majorana fermions, the building blocks for topological qubits that are inherently protected from decoherence. There is huge interest in these for quantum computing. Microsoft's approach hinged on finding Majorana modes in certain nanowires attached to superconductors. Recent results have been mixed, but research continues. More broadly, topological materials enlarge our toolkit. We can have dissipation-less edge channels, useful in metrology, like the quantum Hall effect is used to define resistance standard, or novel phenomena like topological lasers, backscatter immune laser cavities, 2D materials like graphene and beyond. Graphene is a one-atom-thick sheet of carbon that gained fame for its strength, conductivity, and peculiar electronic structure, Dirac cones where electrons act as if massless. Graphene shows at a magic angle of approximately 1.1 degrees, suddenly the electrons strongly interact, and you get superconductivity and other correlated insulating phases. This opened a new field of twistronics, tuning electronic properties by twisting layers to create moire patterns. It's a very quantum phenomenon, Moiré flat bands cause electron interactions to dominate, yielding behavior reminiscent of high TC superconductors, but in a very tunable platform. Researchers are now stacking other combos, graphene with boron nitride, etc., making designer quantum materials where you can alter properties by electric fields or layer alignment. This could lead to new electronic devices, like novel transistors or sensors, or just a better understanding of correlated quantum phases. These are highly entangled states and possibly relevant to quantum information. Some spin liquids could host emergent excitations like majoronimos or anions useful for topological quantum computing. Dot. Quantum magnetism and spin liquids. Some materials have quantum magnetic order, like spins on a lattice that don't order even at zero temperature. A quantum spin liquid. On a practical side, magnetic quantum materials can lead to advances like more efficient data storage. For example, using quantum tunneling in magnetic molecules to make ultra-dense storage, or leveraging antiferromagnetic spintronics for faster memory. They also test our understanding of many-body entanglement, multiferroics and others, materials that combine multiple Org rings, e.g. ferromagnetism and ferroelectricity, in a coupled way. That could allow electric fields to control magnetism, enabling new memory devices right with electric. So on. Read with magnetic. Quantum understanding is needed to tailor these effects. By understanding and engineering quantum materials, we can create devices with novel functionalities. For example, quantum computers themselves might use specially designed materials like superconductors with long coherence, or materials with specific defects as qubits like NV centers, or topological materials to protect qubits, energy transmission and storage, superconductors for power lines, zero loss, or magnets for fusion reactors needing high-temp superconductors. Also, materials for better batteries or catalysts often require understanding quantum chemistry details in solids. Electronics. As silicon transistors reach their quantum limit, few nanometers gates, quantum tunneling causes leakage. We might replace them or augment them with quantum material devices like tunnel FETs, using band-to-band tunneling for steeper subthreshold slope, or spintronic devices, using electron spin and quantum tunneling for memory like MRAM, or ballistic transistors in 2D materials, etc. Communication, lasers and detectors made of quantum materials are central to fiber optics and beyond. For example, the quantum cascade laser is a semiconductor device where quantum well design yields specific mid-IR wavelengths. That's used in free space comms and gas sensing. In some sense, all modern semiconductors are quantum devices. They rely on band structure, which is quantum. But quantum materials push it further. They exploit less classical-like regimes, e.g., coherence, entanglement, topological protection. For instance, a squid is a macroscopic quantum device using superposition of currents around two paths, a Josephson junction ring. It's used to measure tiny fields, sensing as mentioned. A cool emergent concept is quantum metamaterials, structures designed to manipulate quantum states of light or matter in ways not found in nature, leading to, say, negative index for matter waves or improved qubit coupling. To tie to contributions, the development of quantum materials owes to many physicists. From the BCS theory of superconductivity, Bardeen, Cooper Schrieffer to modern condensed matter pioneers. A field thrives on cross-pollination with quantum computing and vice versa. For example, developing better superconductors for qubits, or using qubits like NV centers to probe materials at quantum scale, quantum sensing aiding materials science. In summary, quantum materials research aims to harness complex quantum effects in novel substances to achieve breakthroughs in technology, whether it's perfectly conducting wires, chips that dissipate virtually no heat, or entirely new forms of electronics. Quantum computing itself can be seen as harnessing a material, the qubit medium, for computing. This area is both deep science and potential big impact. Now, as we've covered quantum computing, communication, sensing, and materials, we see that quantum physics is spawning a suite of new capabilities. It's not just about weird abstract ideas, it's fueling real innovations. Some already around us: atomic clocks, MRI, lasers; others on the horizon: quantum internet, fault-tolerant quantum computers, etc. All these applications still ultimately trace back to the fundamental quantum principles we talked about in Section 2. That's why understanding those basics wasn't just an intellectual exercise. It was laying the groundwork for how they change our world. At this point, let's shift gears a bit. We've seen what quantum physics does for technology. But quantum physics also forces us to confront deep questions about the nature of reality, causality, and even possibly consciousness. These more philosophical implications are intriguing to ponder, especially as you wind down listening to this. In the next section, we'll reflect on what quantum mechanics might be telling us about reality itself and our place in the universe, as well as mention some musings on the connection, if any, between quantum physics and consciousness. Take a moment to marvel. The device you're using to listen might itself have components, transistors, LEDs, that only work because of quantum mechanics discovered 100 years ago. The future might bring devices that explicitly say quantum on the label. A quantum phone, secure from eavesdropping, or a quantum coprocessor in your PC solving optimization tasks. We are straddling eras where the quantum is moving from theory to the engineer's toolbox. It's quite the quantum leap indeed. Understanding quantum physics and reality. Quantum physics doesn't just challenge our technological prowess. It also challenges our understanding of reality at the most fundamental level. The theory raises questions that border on philosophy. What is reality when a particle can be in many states at once? Does an observer's consciousness play a role in making things real? Is the universe constantly splitting into multiple worlds to accommodate quantum possibilities? These are profound issues that the brightest minds have debated since quantum mechanics' inception, and there is still no consensus. In this section, we'll gently explore some of these interpretations and philosophical reflections. The goal isn't to answer them definitively. No one can claim that yet. But to appreciate the wonder and mystery quantum physics brings to our understanding of existence. It's a chance to reflect, as you relax, on how strange and beautiful our universe is as revealed by the quantum. The nature of reality, observer effect, determinism versus randomness. One of the most striking lessons of quantum mechanics is that observation matters. In classical physics, we assume there's an objective reality out there, Measuring it merely reveals that pre-existing reality without fundamentally altering it. If a tree falls in a forest and no one hears it, space reeks. In classical thinking, it definitely fell and made sound waves. It doesn't require an ear to generate those waves, just to perceive them. But in quantum mechanics, it sometimes seems that if no one hears, observes, the proverbial quantum tree, it's not settled whether it fell or not. Until measured, a quantum system exists in a superposition of possibilities. The act of measurement, the observer effect, appears to collapse the superposition into a definite outcome. This raised the puzzling question, what counts as a measurement or observer? Is it a conscious mind, or any interaction with a large environment? Bohr and the Copenhagen interpretation took a somewhat pragmatic stance. They posited a divide between the quantum system and the classical measuring apparatus, and essentially said that when a measurement happens as defined by when a classical outcome is recorded, the wave function collapses. They tended not to ascribe a role to consciousness, just the irreversible act of amplification in a measurement device. Wigner posed a thought experiment, Wigner's friend, where you have a friend perform a quantum experiment in a lab, say Schrödinger's cat in a box, while you outside consider the whole lab as a quantum system. However, some like physicist Eugene Wigner wondered if consciousness might be special in this process. From your perspective, before you open the lab door, the friend and cat might be in a superposition of having seen a dead cat and a live cat. But from the friend's perspective inside, the cat is either alive or dead, and they know it. Whose reality is real? Does the wave function collapse for the friend when they see the result, or only when you open the door and become conscious of it? This gets at whether consciousness is needed to collapse the wave function. Wigner leaned towards the idea that perhaps consciousness has a role in quantum measurement, that the quantum state only becomes real when observed by a conscious mind. This view is not mainstream, and most physicists would say an observer could be any sufficiently large thermodynamic system, like a Geiger counter, causing decoherence. No consciousness necessary, but it remains an intriguing question philosophically. Is the observer effect implying something about the interplay of mind and matter, or simply the interaction of quantum and classical realms? To clarify what the standard physics stance is today, most scientists favor a decoherence picture, when a quantum system interacts with the environment, which is full of degrees of freedom like air molecules. Thus, by the time any macroscopic measurement apparatus has registered a result, the system is for all practical purposes in a definite state, even if one considers the whole universe's wave function. Still formally in a superposition of outcomes. Photons, etc. Its superposition decays into apparent classical mixtures very fast, decoherence. Those outcomes don't interfere anymore due to decoherence. In that sense, measurement is observer-independent. A camera could record it, no human needed, and you can treat the camera as effectively collapsing the wave function, or at least decohering it. Consciousness in that view just becomes aware of a result that was already fixed at the device level. Nonetheless, the philosophical mystery of why a specific outcome occurs and what collapse truly means, if anything physical, remains open. This ties into the next issue, determinism versus classical physics, especially before quantum, was largely deterministic. Given initial conditions, the laws determine the outcome. Laplace famously said if an intellect knew the positions and velocities of all particles, randomness, it could predict the future exactly. But quantum mechanics introduced a fundamental probabilistic element. When we measure a superposed state, we cannot predict with certainty which outcome we'll get, only probabilities. Einstein hated this. His quote, "God does not play dice with the universe," encapsulated his discomfort. He believed there should be underlying variables or laws making it deterministic. Not truly random. Bohr and others retorted that indeed, chance is fundamental. Nature at its core is probabilistic. Experiments like Bell tests have strongly indicated that no local hidden variables can exist to restore determinism without contradicting observations. So, if one accepts quantum mechanics, one accepts a degree of fundamental randomness. Every time a nucleus decays, there's no determining the exact moment. It's inherently random, following a probability distribution. The universe, at least in outcomes, appears not fully prescripted, but partly governed by chance. This raises big questions. Does this randomness percolate up to the human scale? Largely no. Everyday objects have so many particles that their aggregate behavior is effectively deterministic by law of large numbers, etc. Plus decoherence ensures quantum randomness averages out or stays microscopic. But at small scales or special systems, like maybe in some brain processes if they were sensitive to single quanta, philosophers and physicists debate whether this has anything to do with free will. Is the brain were classical? It's a biochemical machine, deterministic or chaotic, but essentially determined by prior state. If some brain processes were quantum and truly random, which is debatable, quantum randomness could in principle inject indeterminacy. That introduces spontaneity, but not necessarily meaningful will, just randomness. Still, the mere idea that the universe isn't a clockwork and has genuine unpredictability at its core was a revolutionary philosophical shift from classical determinism to a more indeterministic worldview. So either fully solves the philosophical free will issue straightforwardly. As one interpretation, the universe is not a block of preordained history. There is a fundamental element of chance that, for instance, determines exactly when an excited atom will emit a photon. Einstein. Period. But so far, quantum theory stands, and its random predictions have been proven extremely accurate in statistics. No subtheory has shown those results to be determined by hidden parameters that we just don't see. As we mentioned, refuse to accept this as ultimate truth, hoping a deeper theory might restore determinism. Accept exotic non-local hidden variables which would bring their own strangeness. So are events caused or partly uncaused? In quantum events, we would say they are caused in terms of the probability distribution. Example, the half-life of an atom is a cause for a certain statistical rate of decays. But which particular atom decays at which moment isn't caused by anything specific in standard quantum mechanics. It just happens. This is deeply unsettling if one seeks a fully orderly cosmos, but it might also be deeply liberating. The universe has spontaneity. Novelty is possible. Another aspect of reality questioned by quantum mechanics is locality and realism. Bell's theorem and experiments showed that any theory consistent with quantum predictions cannot have local realism. you must give up either locality, no instantaneous influences, or realism, the idea that physical properties have definite values before measurement. Most physicists give up realism in the quantum sense. They'd say particles do not have a definite position or momentum until measured. The wave function is the reality, which is not a single value, but a spread of possibilities. Einstein would have rather given up locality. He leaned toward hidden variable theories like bombs, which are non-local but keep a form of realism. Either way, our classical notion of an independent reality out there with definite properties, existing whether or not we observe, is deeply challenged. As Heisenberg put it, what we observe is not nature itself, but nature exposed to our method of questioning. Our interactions with a system partially define what we can say about it. Reality in quantum mechanics is closely intertwined with the context of measurement. This gave rise to slogans like, "No phenomenon is a phenomenon until it is an observed phenomenon," John Wheeler. Some take it to almost mystical lengths, suggesting consciousness creates reality, but it could be more measured. It may simply be that quantum events don't have single outcomes until interacting with the macroscopic world, with or without a conscious observer. In any case, quantum physics made scientists much more cautious about what they mean by reality. We now often speak of the wave function or quantum state as a complete description of a system, and prior to measurement, it doesn't make sense to ascribe classical properties as if they were actual. It's not just a lack of knowledge, epistemic uncertainty. It's that the properties are not definite, ontic indeterminacy, until measured. This leads us directly into interpretations territory, notably many worlds interpretation. Parallel universes? One way to interpret quantum mechanics without wave function collapse being random is the many worlds interpretation, MWI. Proposed by Hugh Everett in 1957, many worlds says the wave function of the universe always evolves deterministically and never collapses, when a measurement seems to happen with multiple possible outcomes. All outcomes actually occur, but in different branches of the wave function, which you can think of as parallel universes. Essentially, the universe splits into multiple copies whenever a quantum event with multiple results occurs, each copy reflecting one of the results. In each branch, observers see a definite outcome, but there is an equally real other branch where a different outcome happened, and another version of the observer saw that. These branches can no longer interact. They decohere, losing coherence between them so they don't affect each other, effectively separate worlds. Thus, every quantum choice spawns new universes. This sounds like sci-fi. Prac. But it's arguably a straightforward reading of the mathematics if you take it at face value. Many worlds removes the special role of the observer. No collapse, just unitary evolution of one big wave function. It removes true randomness at the fundamental level. Everything happens, but you, as an observer, experience one path according to probabilities that turn out to match the quantum rules. It's a fully deterministic and local theory. The wave function evolves by the deterministic Schrödinger equation, but it's non-intuitive because it implies myriad constantly splitting realities. For example, in a many worlds view of Schrödinger's cat, before opening the box, there is one world where the cat is alive and one where it's dead. So on, superposed. Opening the box entangles you with the cat's state, resulting in one branch of the wave function where you see a live cat, And in that branch, from your perspective, the wave function collapsed to live, and another branch where you see a dead cat. Both branches are equally real, but they cannot communicate or sense each other, so each observer in each branch is only aware of their outcome. To them, it looks like the wave function collapsed randomly to that outcome. But in the grand scheme, both happened. In many worlds, nothing collapses, everything persists. It's a kind of extreme realism. The wave function and all its parts are real rather than just one part upon measurement. Does this mean literally gazillions of universes? Potentially, yes, effectively an ever-branching tree of outcomes. Some find that extravagant. If quantum mechanics hasn't shocked you, you haven't understood it, as Bohr said. And many worlds is shocking indeed. Others say it's not adding anything extravagant. The math already had those possibilities. You're just saying they all exist rather than only one. Many worlds has gained traction among a subset of physicists and is taken seriously, though it's also untestable directly, since by construction, branches don't interfere once decohered, except maybe in some contrived circumstances if one could recombine them. But for macroscopic events, that's effectively impossible. It also raises interpretive questions like, how do probabilities emerge? If everything happens, why do we experience the probability rules? There are answers using decision theory and measure of branches. And what counts as a separate world, since in principle the wave function is continuous? There are other interpretations too. Copenhagen interpretation, the traditional don't ask, just calculate view that collapse happens and quantum mechanics only gives probabilities for observations. It avoids ontology, doesn't say what the wave function is, just how to use it. Bohr emphasized the cut between classical measuring apparatus and quantum system, complementary descriptions needed for wave versus particle, etc. This was the dominant view historically, though it's somewhat fuzzy philosophically. Pilot wave, de Broglie-Bohm interpretation, an alternative Einstein would have liked. Here, particles always have definite positions. Guided by a pilot wave, the wave function, it's deterministic and realist, but explicitly non-local, because the pilot wave guiding one particle depends on positions of others instantaneously via the wave function. Entanglement. It can reproduce quantum predictions exactly, but it requires a quantum potential that acts in a non-local way. Some find it conceptually appealing, no collapse, reality of particle trajectories. Others find it contrived or philosophically troubling because of the required non-local hidden variable. It's a consistent interpretation, though. It makes different philosophical trade-offs than many worlds, keeps one reality but adds hidden variables and non-locality. Objective collapse theories. These modify quantum mechanics to have actual collapses as a physical process. Randomly, wave functions collapse beyond a certain mass or particle number scale, thus resolving why we don't see macroscopic superpositions. An example is GRW, Gherardi-Rimini-Weber, which posits spontaneous localization events rarely. These theories aim to be testable. For instance, they predict slight heating of matter due to collapse events or some deviation in interference experiments for large masses. So far, no evidence of spontaneous collapse beyond normal decoherence, but experiments are reaching regimes to test them, optomechanics with massive superpositions, etc. If found, That would mean quantum mechanics is not complete as standard, and an actual physical collapse mechanism exists. Relational interpretation suggests that properties are only meaningful relative to an observer. Different observers might give different accounts, like Wigner versus Wigner's friend. It's a more radical reality is relational view, which some say resolves paradoxes by eliminating an absolute state of a system. Quantum Bayesianism, an interpretation that treats the wave function as a user's personal information, like a Bayesian probability, about a system. Not an objective thing. It's an anti-realist approach in a way. Quantum mechanics is just a tool for agents to make bets on their measurement outcomes. This avoids paradoxes by saying the wave function collapse is just the agent updating their knowledge. It aligns with a subjective view of probability. It's a rather philosophical standpoint that a number of people adhere to, focusing on experience and decision. Many others, many minds, consciousness causes collapse, etc., each with various appeals and issues. The bottom line? There's no single universally accepted interpretation of quantum mechanics. This is remarkable. We have an immensely successful theory in practice. But what it means about reality remains unsettled. Richard Feynman famously said that trying to understand what quantum mechanics means, interpretation, might be futile. I think I can safely say that nobody understands quantum mechanics, meaning we can use it but not intuitively grasp it. For a curious mind, this means quantum physics leaves room for philosophical exploration. You might personally lean towards one interpretation or another, but as of now, they're all on the table since they make similar predictions for usual experiments. Perhaps future experiments, e.g., quantum gravity, or seeing how quantum theory and gravity unify, might favor an interpretation or require a new one. What about our place in the universe, then? Quantum mechanics challenges classical ideas of cause-effect and objective reality in some ways, as we've discussed. It suggests the universe at fundamental scales doesn't follow the crisp logic we evolved to navigate the classical world. It's stranger. At its roots, reality seems to be described by a mathematical wave of possibilities, not definite things in definite places doing definite motions. That the solidness of the world emerges from a blur of probability is quite profound. It reminds us that our direct sensory experience is only an emergent layer of truth. Underneath it is a substrate that defies common sense, yet must be true because without it, we can't explain why. The sun shines or why atoms hold together. Quantum tunneling and zero-point energy and so on are critical to these things. Quantum mechanics also revived a sense of mystery and humility in science. In the late 19th century, some thought physics was nearly complete, just refined some measurements. Then quantum theory and relativity upended that view, showing new lands of knowledge. It reminds us our intuitions, formed in a mesoscopic, nearly classical environment, are not a reliable guide to the very small or very fast or very heavy. So, it expands our mind to think of wave-particle duality or entanglement as features of existence. It's almost spiritual for some, not in a supernatural sense, but in eliciting awe at how unintuitive yet elegant nature is. Let's touch on one last speculative idea, which often fascinates people, though it's not mainstream science yet. Consciousness and the quantum. There have been various speculations connecting quantum mechanics to consciousness. This is highly controversial, and no evidence currently shows that quantum effects are directly responsible for consciousness or cognition. Mainstream neuroscience explains mental processes largely in classical electrochemical terms in neurons. However, the speculative ideas are intriguing to outline, with the caveat they are not established science. One famous proposal is by physicist Roger Penrose and anesthesiologist Stuart Hameroff, called OR, Orchestrated Objective Reduction. Penrose, on theoretical grounds, believed that human consciousness involves non-computable processes, insights, etc., which he argued cannot be captured by algorithms per Gödel's theorem. And he suspected the brain might be utilizing some form of quantum gravity-induced wave function collapse, objective reduction, as a mechanism for consciousness. He teamed up with Hameroff, who suggested microtubules, protein structures in neurons, as sites where quantum coherence might be maintained and orchestrated by biology to influence neuronal activity. They proposed that when enough mass displacement in microtubules occurs in a coherent superposition, Penrose's gravity-related collapse triggers objective reduction, and the collapse might even be influenced by Platonic values or some non-computational factor, thus linking quantum events to cognitive processes, yielding a moment of conscious awareness. This theory is very controversial for numerous reasons. Maintaining quantum coherence in the warm, wet brain seems implausible, though some evidence of quick coherent vibrations in microtubules was claimed by some researchers. And there's no experimental validation that consciousness works this way. It remains a fringe idea, albeit championed by a few. Another related idea is that quantum entanglement or tunneling might play roles in neural processes or in how we experience free will or unity of mind. So far, no conclusive evidence. Some interesting results exist in biology where quantum effects are at play. E.g., photosynthesis efficiency might use quantum coherence to transfer energy, observed in bacterial systems at low temp. Observations. Debated at physiological temp, but that's not about consciousness, just biology using quantum physics. Birds use quantum entanglement in a protein, cryptochrome, for magnetoreception, navigating Earth's magnetic field. That's a real quantum biology example. Entangled radicals in a bird's eye reacting to magnetism. But again, that's sensing, not conscious processing. Philosophically, some have mused that perhaps the mind-body problem, how subjective experience arises from matter, might find some resolution in quantum theory. Maybe our conscious mind is correlated with a quantum state that isn't bound to one location, etc. But these are speculative and not grounded in testable hypotheses yet. Most scientists working on consciousness do so in a classical framework, neuroscience, cognitive science. A more metaphoric connection, people sometimes say quantum indeterminacy could leave room for free will because not everything is predetermined. However, randomness is not will. It's tricky, perhaps a mix of deterministic neural processes and some quantum randomness could give a non-predetermined outcome. But is that you making a choice, or just a dice rolling your head? That's philosophically murky. Interestingly, the act of observation in quantum mechanics inspired some to think about the role of consciousness in reality. For instance, John Wheeler even pondered a participatory universe where conscious observation is necessary to bring the universe into being. He illustrated this with the delayed choice quantum eraser thought experiments, where choices made now seem to affect the past outcome, but not really just how we parse information. Wheeler suggested we might live in a kind of quantum participatory universe where observers are necessary parts of the fabric, the universe observing itself. This is more philosophical poetry than testable science, but it speaks to the wonder that quantum mechanics evokes. We should clearly state these consciousness-related ideas are speculative. They are not mainstream, and one should not conclude that quantum physics has proven anything about soul or consciousness or the like. But it's an area where curiosity abounds. It crosses into philosophy of mind. Is the brain just a classical machine, with any quantum effects negligible? Or could quantum phenomena be relevant, like maybe in synaptic vesicle release there's some quantum randomness affecting neural circuits, etc.? Right now, no evidence compels us to invoke quantum processes for explaining cognitive neuroscience. Classical models do a decent job for everything measured. Hammer-of-Sperry would predict some specific things, like anesthetics affecting microtubule quantum states, etc., but evidence hasn't concretely supported that. From a more practical angle, one could ask, if we eventually build a quantum computer as complex as a brain, would it be conscious? Or does consciousness require certain quantum processes? That's open-ended and relates to bigger questions. What is consciousness? If one subscribes to integrated information theory or other frameworks, it doesn't obviously require quantum effects, though some try to integrate those too. To avoid ending in too speculative a note, it's safest to say quantum physics undeniably changed how we think of measurement, reality, and perhaps by extension, raises questions like, what is the role of the observer, which could include conscious observers in the fabric of physics? It doesn't answer them definitively. It may hint that reality is not a fixed set of objects with properties independent of us. Instead, our interaction, our measurement choices, partly defines reality's manifestation. That's a somewhat philosophically empowering idea, that we are not just passive observers of a clockwork cosmos, but participants. As one physicist, Wheeler, said, we are tiny patches of the universe looking at itself and creating itself. He even used the term participatory anthropic principle. The universe requires observers to exist in a meaningful way. That is reminiscent of philosophical idealism. Mind creates reality. But in physics terms, it may simply reflect quantum mechanics' puzzling insistence that how you choose to observe, what basis, what timing, etc. influences the phenomenon. These are deep waters indeed. Late at night, it can make one wonder about the connection between mind and matter. But as of now, these remain wonderful questions rather than settled science. And that's okay. Part of the charm and enduring intrigue of quantum mechanics is that it forces us to confront mysteries that were once solely in the realm of philosophy, but now have scientific context. It keeps us humble and curious. As a final thought experiment, some interpretations, like many worlds, suggest every possible outcome of every decision you didn't take does happen in some other world. There's a world where you chose a different career, or where a historical event went differently. This is like sci-fi, but some physicists seriously entertain it as the straightforward reading of the equations. It's mind-bending and can lead to existential questions. Are there copies of me? Do they count as me? We won't solve that here, But it's quite interesting that a physical theory leads to these questions naturally. Another one, Bell's theorem, implicitly connects to the concept of realism. Is the moon there when no one looks? Most would say, of course. And in practice, it is. Decoherence ensures macroscopic objects have well-defined states. But in principle, if the moon were completely isolated quantum mechanically, which it isn't in reality, one could construct a scenario where it's in a superposition. It's these thought experiments that challenge our intuitions about existence. Physicist and philosopher of science Carlo Rovelli put forth the idea in relational quantum mechanics that properties only exist upon interaction. So, in a sense, no, the moon isn't defined if absolutely no interaction occurs, but that's a purely hypothetical situation. In reality, the moon interacts with the sun's photons, etc., so it has a position. All right. Enough of making heads spin, hopefully gently. The key point is, quantum physics opened profound philosophical debates about determinism, objective reality, and the role of observers. The debate among physicists continues, often not in mainstream research papers, but in foundational discussions, conferences on interpretation, and thought experiments in their spare time. It's a healthy reminder that science and philosophy can intertwine, especially at the edges of knowledge. As the eminent physicist and philosopher Niels Bohr said, everything we call real is made of things that cannot be regarded as real. That paradoxical statement nicely captures the quantum essence. Our classical concept of reality fails at the micro level. Yet from that unreal-seeming quantum world emerges the concrete world we experience. Our place in the universe. From a cosmic perspective, quantum mechanics is not just a human intellectual triumph, but perhaps a hint at a deeper layer of understanding still to come. It underlies why stars shine, quantum tunneling in the sun, why the periodic table has its structure, quantized electron shells, why chemistry and thus life exists, stable atoms needing quantum rules. It even sets alternate limits and possibilities. Heisenberg's uncertainty might eventually limit how precise any measurement can be, but it also gives stability. If electrons didn't have zero-point motion, matter would collapse. In that sense, we are quantum creatures. Our atoms follow quantum laws. We typically just don't notice the quantum strangeness at the macro level. But everything solid, stable, and rich in structure around us is because of quantum rules. There's a quote by physicist Max Born. The quantum theory provides us with a striking illustration of the fact that we can fully understand a connection, though we can only speak of it in terms of probabilities. In other words, it's sobering that everything deterministic and classical is emergent from something probabilistic and fuzzy. We understand nature deeply, yet it defies a simple causal picture. Determinism versus randomness has another layer. Some find comfort that quantum randomness might allow free will in an otherwise mechanical universe. It touches on age-old philosophical and even theological notions. Einstein's dice quote was essentially him saying he believed in underlying order, often misinterpreted as him referring to God. Literally, he meant an orderly universe. Others find it disconcerting those fundamental events have no reason. Bohr responded, "Stop telling God what to do," indicating acceptance of nature's apparent randomness. Each person might resonate differently with these perspectives. The observer effect can lead to almost solipsistic-sounding ideas. If no consciousness is around, does anything happen? I should emphasize mainstream physics does not require a human mind for quantum events. Interactions suffice. But the language and formalism can sometimes mislead people down that path. At this juncture, it's good to recall the quote, "Shut up and calculate," often attributed to Feynman or Merman, urging that we focus on using quantum mechanics rather than philosophizing too much. Indeed, for most working physicists, these interpretation issues rarely affect daily research, except in foundations research. But it's still worthwhile, especially in a reflective or educational context, to ponder these bigger questions. It broadens our perspective and sometimes leads to new ideas. As we end this philosophical segment, remember that quantum physics raises profound questions, but also leaves them beautifully unanswered for now. This open-endedness means there's room for you to think about it too. Even as a layperson or student, you can contemplate interpretations. It's not something only experts have a say in, because no one has the final answer locked down experimentally. Einstein, Bohr, Schrödinger, Heisenberg, they all had different takes and spirited debates, like Bohr and Einstein arguing at Solvay conferences about these issues. Today, Zeilinger, Aspect, Nobelists of 2022, and others continue experimental probes of quantum foundations. That space, closing loopholes in Bell tests, etc., edging us closer to seeing just how weird the quantum world really is, with fewer caveats. For instance, just recently, 2022, the Nobel was awarded for experiments confirming entanglement's reality and violation of Bell inequalities. Essentially, putting the nail in local realism's coffin, spooky action at a distance is a real thing in nature. That's huge philosophically. Einstein's intuitions were proven wrong on that point, and the universe is more non-local in correlations than he hoped. Quantum mechanics and reality's nature will likely continue to fascinate generations to come. Perhaps a future breakthrough, maybe a theory uniting quantum mechanics with gravity, will shed new light on these interpretation questions. Some think gravity might induce collapses, Penrose's idea, or that many worlds might be confirmed indirectly if we ever see quantum effects in gravitational waves or something mind-boggling. Who knows? For now, it's wonderful food for thought while drifting to sleep or in a relaxed state. It gently exercises the mind's capacity to hold two seemingly opposed ideas. Something can be in two states at once, and realize reality is subtler than it looks. Conclusion: the quantum age dawns. We've traveled from the subatomic strangeness of quantum theory all the way to its grand implications for technology and even philosophy. It's time to gently recap our journey and reflect on what it all means as you relax in this final section. In summary, we began by venturing into a realm beyond everyday intuition, the quantum world. We saw how at tiny scales, particles behave in ways that defy common sense. They can act like waves spread out in space, yet also hit a screen as point-like particles. They can exist in a superposition of multiple states at once, embodying potentialities rather than actualities until measured. Two particles can become mysteriously entwined or entangled, such that what happens to one instantly affects the other, no matter the distance. And particles can do the classically impossible: tunnel through barriers they shouldn't cross. These mind-bending basics, quantization, wave-particle duality, superposition, entanglement, tunneling, form the core of quantum mechanics. While bizarre, they are supported by a century of experiments and are now understood to underpin the stability of matter and the processes in the universe. We then took a quantum leap into how these principles are changing our world through technology. In the quantum computing revolution, we learned about qubits that leverage superposition to encode far more information than classical bits, and entanglement to perform computations in parallel universes of sort. Recombining them for a single answer, we saw that while full-scale quantum computers are still in development, even the early ones are demonstrating potential, from solving specialized problems much faster than traditional computers to promising breakthroughs in drug discovery include optimization and cryptography. We also acknowledged that we're in the NISQ era. These devices are nascent and noisy, and big challenges like error correction lie ahead. But leading minds and companies are steadily pushing the frontier, and each year brings new milestones: more qubits, fewer errors, new algorithms. It's an exciting unfolding story, one that could drastically reshape computing and allied fields in the decades to come, ushering in what we can truly call a quantum age of technology. Beyond computing, we explored other applications. Quantum communication promises unhackable encryption through entangled photons and quantum key distribution, a way to ensure absolute privacy in an era where classical codes will be threatened by quantum codebreakers. Countries have already exchanged quantum encrypted messages via satellite, a prelude to a future quantum internet that might securely connect the world's information networks. Quantum sensing is enabling ultra-precise measurements, clocks that keep time so accurately they could detect tiny gravitational differences, magnetometers that can probe brain activity or geological minerals via faint magnetic fields, and interferometers that might measure gravitational waves or inertial movement with unprecedented precision. These sensors will likely find their way into navigation systems, medical devices, and scientific instruments, quietly improving performance behind the scenes. Quantum materials, too, are emerging. By mastering quantum interactions in solids, we're discovering new phases like high-temperature superconductors and topological insulators, which could revolutionize energy and electronics. Imagine power lines with zero loss, or electronic devices that dissipate far less heat, or memory that switches by quantum tunneling for ultimate speed. These are the promises quantum materials hold as our understanding grows. Zooming out to the profound questions, we contemplated how quantum physics challenges our understanding of reality. It taught us that the act of observation is not passive. It's deeply woven into what outcomes we see. It introduced fundamental randomness, a built-in indeterminism in the fabric of nature, ending the classical clockwork universe myth. It forced us to accept that particles don't have definite attributes until interacting with something else. And it even opened up interpretations where our universe is constantly splitting into multiple versions to accommodate all quantum possibilities. A breathtaking, if mind-boggling vision of reality. These discussions remain unanswered definitively, showing that even as we master quantum theory's practical uses, we still seek to fully understand what it means about the world. We stand as thoughtful beings, humbled by the realization that reality is far more complex and wondrous than our classical intuition suggests. It's truly remarkable. The abstract quantum ideas born in the early 20th century out of curiosity, Planck's quanta, Einstein's photons, Bohr and Heisenberg's uncertainty, Schrödinger's wave functions, Iraq's equations have now, in the 21st century, become the bedrock of new technologies and ongoing philosophical intrigue. We've gone from puzzling over electrons in atoms to intentionally placing objects into quantum superposition in the lab to exploit that behavior. On one hand, quantum physics has a very rational side. It's a rigorous mathematical framework that lets us calculate the behavior of particles and fields with astounding accuracy. The fact that we can engineer transistors of billionth of a meter scale reliably is a testament to how well we understand quantum rules for electrons. As we conclude, take a moment to appreciate the mystery and marvel inherent in the quantum story. On the other hand, quantum physics teaches us intellectual humility. Whenever we think we've figured out the universe, it reveals another layer of surprise. It invites us to wonder about questions like, are there deeper laws beyond quantum mechanics? How does it unite with gravity, a puzzle yet to be solved? Will understanding that give us even crazier technology or insights, like maybe traversable wormholes or understanding the Big Bang? We don't know yet, but quantum theory will surely be central in any progress there. So where are we now? We stand at the dawn of the quantum age, where the weirdness is not just a subject of thought experiments, but a practical tool. The coming decades may see quantum computers tackling problems that stumped classical computers, quantum sensors peering into realms previously inaccessible, and quantum communications safeguarding our digital world. Perhaps our children or grandchildren will think of classical computing much like we think of the abacus, quaint but limited, as they use powerful quantum processors for their tasks. The transformation could be as pervasive as the semiconductor revolution, albeit behind the scenes for many. Yet, even as quantum technology becomes everyday, may we never lose sight of the almost poetic strangeness at its heart, the fact that every electron in your body is a fuzzy wave that only appears particle-like when interacting. Or that there's a tiny probability as you sit there that some particle in you tunnels through a potential barrier spontaneously. Don't worry, for macroscopic barriers that probability is effectively zero. These facts can instill a sense of wonder about existence. Embracing these quantum leaps in knowledge and technology helps us not only build better gadgets, but also perhaps better understand ourselves and our universe. After all, we too are quantum beings made of star stuff that behaves in quantum ways. In grappling with quantum physics, we're trying to understand the very fabric we're made of, and that's a profound human endeavor. As you relax or drift to sleep after this journey, let your mind ponder these ideas if you wish, but also feel a sense of calm awe. The universe is a mysterious, magical place governed by elegant rules that we are slowly uncovering. It's okay that it's counterintuitive. Our intuitions were forged for survival in a mid-sized world, not for comprehending atoms or galaxies. Yet somehow, through creativity and reasoning, We have uncovered these truths and even harnessed them. It shows the power of human curiosity and intellect. In closing, remember that every technological quantum leap started with a leap of imagination. The scientists who first theorized these ideas often faced skepticism or confusion. But by staying curious and open-minded, they ushered in new understanding. In your own life, there may be times you need to take leaps into the unknown, whether in learning, career, or personal growth. The quantum story encourages us that embracing the unfamiliar can lead to remarkable outcomes. So as you gently close your eyes, if you haven't already while listening, think of that electron in a superposition, or that pair of entangled photons spanning two cities, or the quantum computer that might one day solve a medical puzzle overnight. Think of how far we've come from the time when electrons orbiting nuclei were a total mystery. We journeyed from curiosity to comprehension to application, and there's so much more ahead. Thank you for joining this exploration of quantum physics. I hope it brought you both knowledge and a sense of wonder. Feel free to drift off contemplating the dance of particles and waves, or simply rest with a tranquil mind, knowing that even as there are mysteries in the world, there is also an underlying order we are gradually uncovering. The universe is full of unanswered questions, and that's a beautiful thing, for it means there will always be more to learn, to imagine, and to discover. Sleep well, and perhaps dream of quantum possibilities. The cat both alive and dead, the electron passing through two slits at once to paint an interference pattern, or you yourself taking a leap into a new world of opportunities. After all, as the great physicist and great thinker Niels Bohr advised, how wonderful that we have met with a paradox. Now we have some hope of making progress. Good night, and welcome to the quantum age.